Alright. Can everyone hear me? Do a quick mic check first. I think there is a bit of lag between me and the stream. So I'll have to wait a bit. Great. Cheers. Okay. Alright. I think we can start now. There's a few people here already. So, welcome to the 1031 revision seminar. This is actually the first time that MathSoc has done a 1031 revision seminar. Before we've only done like the mainstream math courses, but like we're trying to branch out a bit, and so this might be a bit rusty, but we'll see how it goes, and I think it should be pretty good. So these slides were written by Shayak and Donald, but unfortunately Shayak's not here to present his half today, so I'll be taking over for him, and then Donald will be here for the second half of this seminar to present his part of the slides. Yeah, so we will begin now. Okay, first thing to note is that this course is packed with content. Like, it's crazy how much content there is. Like, it's a lot. So, and the thing is, like, in this small 3-hour time slot, we have to kind of get through all of it, like, as much as we can. So I'm gonna be like doing a lot of examples to like get you ready for the exam, speeding through examples, showing some like tips and things like that. But I don't expect it to like sink in on the first go. So if you do have the chance, after like taking notes or whatever, go back and watch the video and like, pause at the right spot to like see the working out. And yeah, hopefully that will get you fully prepared for the exam. Yeah, so for my half, I think I'll be going up to linear equations, and then Donald will take over here. So yeah. Okay, so chapter 1 is... Oh, and I should mention, if anyone has any questions, just drop them in the chat. I'm keeping an eye on the chat as much as I can. And hopefully I'll get to your questions. Cool. So chapter 1 is matrix algebra. So this is like an introduction to what matrices are, how to use them, how to model situations with them. So this first slide is just talking about why we want matrices, right? So and I'm sure like you've been told this in lectures as well, that like we can take data like this. We have a collection of objects in one place, a collection of objects in another place, and another collection of objects in another place. And we can consider these as columns of a matrix, right? So this can be like column 1, column 2, column 3. And we can write this out in matrix form, right? So if we have 3 aardvarks, 2 birds, 4 crabs, then we would say 3, 2, 4. And that's in region 1 or region A or whatever. And then in region B, we have 9 aardvarks, no birds, 2 crabs, and then in the third, hang on, actually I think this was already in the slide, so I don't have to rewrite it. If we just scroll down here, we can kind of see it here, right? So yeah, so you can model situations like this using just a matrix, and that's what we're going to be like looking at in this chapter. So one important thing we can see is that matrices do have like a size attached to them. So you can have a matrix that looks like this, or you can have a matrix that looks like this. And like we call this a 2 by 2 matrix. This is a 3 by 3 matrix. So these things have size, and in general we say m by n. So m is the number of rows, and n is the number of columns. So that's how we classify a matrice's size. We can add matrices together. This is just done like term-wise, and I'm not sure if is there an example? Yeah, there's an example for adding matrices here. So if we have this matrix plus this matrix, what we do in the new matrix, the size will be the exact same. And we take for the 1/1 position, we take the 1/1 position in matrix A and matrix B, add them together, and we get the final 1/1 position. Then for the 2/1 position, we just add the 2/1 positions together. For the 1/2 positions, we just add the 1/2 positions together. It's just term-wise addition. That's all it is. And subtraction works the same way. So if it was subtract, then we would just put a minus here and we would just minus the terms. We can also define multiplying a matrix by a scalar. So here we have a 3 by 4 matrix, and we have this scalar 4, and we are multiplying 4 to this 3 by 4 matrix. What this means is we're going to multiply every single term inside of this matrix by 4. So we're going to do 3 times 4, 2 times 4, blah blah blah, minus 8 times 4, 4 times 4, blah blah blah, blah blah blah. And this is what we end up with. So every term's been multiplied by 4. And it doesn't matter like what order we multiply a scalar by. So like we can have 2, 1, 3, 3 times 4, and that'll be the same as 4 times 2, 1, 3, 3. Like these two things are the same. This might seem a bit weird because like in real numbers, when we're doing like normal multiplication, like 2 times 3, that's the same as 3 times 2, of course. Matrices work a bit different. So for matrices, multiplication isn't like that. So we're defining a new type of multiplication that's special to matrices. Okay, so the definition is a bit confusing, so I'll do a cool trick instead that might get the point across. So let's do like a 3 by 3 matrix. And let's multiply this by, I don't know, like 1, 1, 2. Okay, how would we multiply this? Well, what you do is, if I can highlight it, that would be easier. What you do is you take this row and you multiply the terms in this row by the terms in this column, and the sum will give you the first entry. So the first entry in our matrix would be row 1 times column 1. So it'll be 1 times 1 plus 2 times 1 plus 3 times 3. So that should be 12, correct me if I'm wrong. And so the first entry in the 1/1 position is 12. For the second entry, you take row 1. So okay, so this entry now that we're going to look at next is going to be this one here, and this is the 1/2 entry. So the 1/2 entry, this corresponds to the first row of the first matrix, multiplied by the second column of the second matrix. So we're going to do 1 times 1 plus 2 times 2 plus 3 times 1. Okay, so that's 1 plus 4 plus 3. So this should be 8. And then for the third one, you just take the first row and you multiply onto the first row. I don't know what's good color. I'll do that. The third column this time. Okay, and you keep going. So for the 2/1 term, you take the second row and multiply it by the first column. And in general, for the bth entry, what you do is you take the 8th row and you multiply it by the bth column from the respective matrices. Okay, I think you guys have like a lot of practice with matrix multiplication, so I won't like stick too much to this, and I'll trust that you guys know what's going on there. And like I mentioned before, it's not commutative, which just means that AB doesn't always equal BA. So you do have to be careful when you're multiplying matrices with the order. The order matters here, definitely. Here's an example to show when matrix multiplication doesn't work, okay? So we have a matrix A here and a matrix B here, and we want to find AB. Well, the thing is, A has size 3, 3, and B has size 2, 4. And we can't multiply these, so this is invalid. And the reason why is because matrix multiplication is only defined if the first matrix has size mn and the second matrix has size np. So p and m can be whatever you want, and n has to be the same. So like the number of columns for the first matrix has to be the number of columns for the so the number of columns in the first matrix has to be the number of rows in the second matrix. Yeah, there you go. So keep that in mind when you're doing matrix multiplication. Make sure you're not multiplying invalid things. And if you look here, like, you can kind of see why it's not defined for these kind of matrices, right? Because if you take this row and you try and multiply it by this column, this 3 is going to feel left out. And so that's why we define it as it is. Okay. So here's a valid example of matrix multiplication. It's just a lot of calculations, and I trust you have a calculator to do things like this quickly. But yeah, so it's exactly as you'd expect from earlier. So let's look at some special matrices. So we know matrices are a thing now. Let's have a look at some specific examples of matrices that we'll see often. Here's a zero matrix. I don't think you'll see this often actually, but it's still nice to know. This is just when everything is 0. One thing you can see is that multiplying a matrix by a, well, we call this a vector technically, but it's still a matrix. Oh, it's gone into auto writing mode. And multiplying a non-zero matrix by a non-zero vector can still give us something that's zero. So that's an interesting property of the zero matrix. So you can see that it pops out. This one you'll see a lot, the identity matrix. So this is the 2 by 2 identity matrix, 3 by 3 identity matrix, 4 by 4 identity matrix. It's so the way you make it is just make all of the diagonals 1 and everything else has to be 0. And we call this the identity matrix because, like in real numbers, when you do something like 3 times 1, you get 3 out, right? Well, in matrices, when you take a matrix and you multiply it by the identity matrix, you just get the matrix itself back. So this I is kind of like the number 1, but in the matrix world. And of course, you need to be careful with the size here, as it says down here. So it needs to be this the appropriate size. So you can only multiply matrices that look like this in size. I'll probably switch back to blue. Forgot to do that. Okay. So here's another important use of matrices that we're going to need, so the inverse matrix. So if you have a matrix A, it can sometimes have something called an inverse, meaning some matrix, when we multiply it by A, we get the identity out. So this is kind of like with normal numbers. If you take a number like 3 and you multiply it by 3 to the power of minus 1, you get 1. So we're kind of copying this into the matrix world, and we're saying, okay, if you have a matrix A, we want to find some sort of matrix A inverse so that we get the identity out. And the hard part is, how do we find A inverse? And does A inverse even exist? Like, is it possible to find a matrix that does this? Well, we'll see. We'll see. So first thing to note is that I should probably give you some proof that this does happen. So here's an example, right? So A times B will give you 1, 0, 0, 1, where A is this, B is this. So here's one way you know if a matrix has an inverse or not. It has to be square. So that means it has to be size m times m. You can't have different rows and columns. Like, you can't have a different number of rows than to columns. So it needs to be square. That's your first condition. But we can't just stop there, because not all square matrices even have an inverse. Like, for example, the matrix 1, 2, 1, minus 2 won't have an inverse. Hang on, that should be plus. That won't have an inverse, right? Okay, so you need to be careful, even though it is square. So how do we find inverses? Okay, let's have a look. So we usually use this thing called Gaussian elimination, which you've already seen throughout the course. Or black magic, I guess, which is just like further maths. But you don't need to worry about that, because in this course, you're only ever going to be asked to find the inverses of 2 by 2 matrices. And we can find the inverse of a 2 by 2 matrix easily using this formula. So keep this formula in your head at all times, because it's super useful. And it's actually one of the few formulas that I actually recommend just knowing by heart, okay? And you can see, like, this is one of the conditions for there to be an inverse or not. So AD minus BC, if it's 0, then you can't have this, right? Because then you'll be dividing 1 by 0, and that's bad. It's bad news. So that's how I knew that this matrix here didn't have an inverse. Because if you do 1 times 2 minus 2 times 1, you get 0. So no inverse. So you need AD minus BC to not be 0. Great, okay. So here's one more, and I think this is the final one. So here's one more example of a matrix operation that we can do. So we call this a transpose. So it might sound fancy, but really what it is you take a matrix like 1, 2, 3, 1, 0, 0, and to find its transpose, you just switch it over to its side. You just rotate it to its side. Okay, so its columns are now its rows, and its rows are now its columns. That's all it is. And here's a basic example, of course. So all we're doing is we're just turning the matrix onto its side. Okay, so that's all for matrices. We're going to use them heavily in modeling and in algebra when we get there. So keep this in the back of your mind for now while we take a detour into calculus. So, okay, first part in calculus, we need to know what functions are. Well, functions are exactly as you'd expect them to look from high school if you've seen them. It's just some y, which could be an f of x, right? And it's just defined in terms of x. So whatever x you put in, you'll always get one value for y. And we sometimes call this y a dependent variable, and this x as an independent variable, because what's happening here is we're changing x to change y, and y really just depends on x. And that's why these are like really good tools for modeling as well, so we'll see that soon. Okay, to move forwards, we do need to learn some new notation, and what this is it's called interval notation. Okay, so if you have some interval, so for example, from -5 to 5, if you have x between -5 and 5, then we write it like this. These square brackets signify that it's a less than or equal to relation. If it was just less than without the equal to, then we would do a round bracket on both sides if it was like that. If it's less than or equal to on one side and less than on the other side, then we do a square bracket on the side that it's less than or equal to, round bracket on the side that it's just less than. And if we don't have a lower bound, then we just do a round bracket with infinity. And similarly, if we say like t greater than 1, then we would write this as 1 infinity. Okay, I won't dwell on that too much. You probably have seen that notation throughout the course. Okay, so there's a lot of information here, so let me try and break it down. What we have here is, we want to know these two words. We want to know what a domain and a range are. Okay, so for a function, I'll choose something a bit easier actually. I'll go like y equals square root of 1 minus x. Let's have a look at this. So the domain is the set of values for which we can define a function, okay? So for this function here, we can't have a negative thing inside of the square root, right? So that means that this 1 minus x has to be positive or 0. And this just means that x has to be less than or equal to 1. So the domain is this thing here, x being less than or equal to 1. And to write it in set notation, you can use our set notation knowledge from the previous slide. We would write it like this. So that is the domain. The range is the values that the function can possibly take. So we know that we know for y equals square root of 1 minus x, we know that the square root will always give us something positive. Okay, so whatever we have here, we're just taking the square root of that, and that's a positive number. So this has to be greater than 0 or equal to when x is 1. As x goes to minus infinity, this whole thing will go to infinity. So this is equivalent to saying 0 infinity with a square bracket this time because it can equal 0. And that's what we call our range. So it's the set of values that our function can spit out. Cool. Here's some ways that we can manipulate functions. So if we have a function f of x, we can multiply it by a scalar c to kind of stretch the function out. And we call this scaling. So for example, if c is greater than 1, then the graph is actually stretched in the vertical direction. So you can kind of think of it like if we had a graph that looked like this, we multiply it by a c that's greater than 1, then it would end up, if we multiply it by c, it would be stretched out more. Okay, and if we multiply the graph by some c between 0 and 1, then we're actually shrinking it vertically, and it would look like it would be shrunk vertically, okay? If c is negative, then both happen, except we also flip it vertically. So if c was negative, and c was less than or equal to, if c was negative and between 0 and minus 1, then what would happen is you'd get something like that. Oh, actually, wait, hang on. Flipped it the wrong way. So it would look like that, right? There you go. Okay. You can also scale the x values. So instead of putting the c out here, we can put the c inside of here. And what this does is that it'll shrink it horizontally if it's positive. So if c is not positive, sorry, if c is greater than 1, then what happens is if we have a graph that looks like this, then what it'll end up looking like, well, we have to shrink it horizontally this time. So it'll be kind of squished. But then if c is between 0 and 1, then the graph will be stretched, meaning it'll kind of look like that now. And if c is negative, then we do the same thing, but now we also flip it horizontally. Okay, so if you notice with the y values, being greater than 1 means stretching, being between 0 and 1 means shrinking. Well, with the x values, it's just the opposite. So it's a bit annoying to remember, but yeah, that's how it is. Yep, okay. So we can also shift the values. So if we have a plane and we have a graph on this plane, it's a terrible graph, why did I do that? Then we can shift it to the side to look like that, maybe. And we can also shift it upwards if we wanted to look like that, or downwards to the left. And the way we do this, okay, so vertical shifting, you just add some c onto your function. And horizontal shifting, you take away some c from the inside of the function. And again, this is annoying to remember because you're adding c here and you're minusing c here, okay? But the trick I like to use is that instead of thinking of it like this, think of it like y minus c equals f of x, okay? and then here you still have y equals f of x minus c. So whenever you want to shift by c, you really just need to take away c from one of the variables. That's how I like to that's how I like to think of it, and I think that makes it a bit more clearer. Okay, so this is something we call a piecewise function. So a piecewise function is same as your normal function, except we now have this big black bar here, and we have a bunch of different intervals, and we define our function differently on each interval. So for x less than or equal to 3, this function looks like x squared. For x between 3 and 6, this function looks linear. For x greater than or equal to 6, this function is an oscillator. So this is really useful because in real life, things don't act like just one function, right? Things can, in one time period, it can look like this. In another time period, it can kind of stagnate, and then it can drop off, and then it can keep going upwards exponentially. Like, it can look like a bunch of different things, okay? So that's why we have piecewise functions. And so here's the graph of the piecewise function we saw earlier. So here, x squared for x less than or equal to 3. So let me draw 3 on the axes. So before 3, it looks like a parabola. Between 3 and 6, it looks like a line. And then from 6 onwards, it's oscillating. And so this could potentially be mirroring some sort of real-world application here. And that's kind of like the point of why we like piecewise functions. So here's a cool version of a piecewise function. So periodic functions are really kind of like piecewise functions. You can think of them. What they are is some function where if you add a period to it, it'll come back to its original spot. So the classic example is, of course, sine, right? So whenever you add 2 pi into the sine function, it just returns back to its original thing, because sine of theta is equal to sine of theta plus 2 pi. Adding 2 pi doesn't change it. So this is the classic example of a periodic function. And there's many types of periodic functions, really. So, for example, maybe one that might be more realistic to real world, rather than this smooth sine curve, is something that looks a bit more jagged like this. Things like that, okay? So these pop up everywhere in science, and it's really nice to know periodic functions well, because you'll see them a lot. Right, so here's the classic 2 examples of periodic functions, sine and cosine. So here you have sine, here's cosine. As you can see for cosine, right, so its value here is the same as its value here, is the same as its value here. Sine, its value here is the same as its value here and here. And you can do this with any number of spots, right? Because from here to here is the exact same as from here to here. And for cosine, from there to there is the exact same as from there to there as well. So these are examples of periodic functions. They act the exact same wherever you go. Alright, so when we're dealing with angles in sine and cosine functions, and sine and cosine functions are still going to come up a lot in periodic functions, and you'll see why later. So when we're dealing with angles, we tend to not really like degrees that much, because degrees can be a bit weird, and it's a very arbitrary choice of measurement, like y360, right? So instead, we like to think of things in pi. Pi comes more naturally, because when we think of an angle, what it really is, if we think of an angle here, it's really just a chunk of a circle. Okay, and that's why we like to think of it in pi, because if we go around full circle, we travel 2 pi, which is actually the circumference of a unit circle. Okay, so that's why we like to think of things in pi, and we call this measurement radians. So conversion between radians and theta, between radians and degrees, as you can see here. So if you have r radians, then you just multiply it by 80 on pi, and you get the degree out. And if you want to get the radian from the degree, then you take the degree and you multiply it by pi on 180. So that's how you convert from degrees to radians. Okay, we're going to use our radians straight away now. And we've constructed this table here of our normal trig functions, and we're just plugging in different angles, okay? And it's important to know some of these values because they can come up a lot, but I think your calculator will give you these as well, so it should be fine. And I think you guys already know most of that. Okay. So with sine and cosine functions, we need to know about compound angles. This is when you have two different angles inside of your function. So sine of a plus b is sine a times cos b plus sine b times cos a. And if this is a minus b, then here you just change the plus to a minus. And then cos of a plus b is cos a times cos b minus, so if this is plus here, then this has to be minus sine a times sine b. And if this is, I'll do it in a different color, if this is a minus here, then this has to be a plus. So that's what this, because this looks like a plus minus, right? But over here, this is a minus plus because the minus is on the top. That's what that signifies. And I'll erase that to make it a bit more clearer. And then finally, the tan double angle formula is, so you have a plus b. So on the top, the sign stays the same. On the bottom, you have to change the sign. Okay. So those are really easy mistakes to make, forgetting how the sign goes. Okay, so this is what we call an auxiliary angle formula. So if you have some sort of combination of trig functions like 3 sine plus 5 cos, you can actually combine them into one sine or cos function, like this. And you'd be right to guess that it comes from Pythagoras' theorem. So that's why the r looks like this, and alpha looks like this. Okay, so alpha is really just, well, you make this triangle, right? And you have alpha here, and the coefficient of sine and cosine will go on the sides, okay? So this would be b, this would be a here, and this would be r. And so you need to find r and alpha and put them into these equations. So that's how we can kind of shrink a combination of sine and cosine into just one compact curve. Okay, so here's another interesting example of a function called a logarithm. Okay, so logarithms kind of came out of the problem of having to solve equations that look like a to the x equals b. How do we solve this? Well, what we did is we kind of created our own solution. Okay, we said, this is log b of a. What this means is, if you ever see this, what this really means is that a to the power of x will give you b. That's all it is. So it's just fancy notation for that. And I think that's kind of explained here. So logarithms have some special properties, okay? So I'm gonna, for these parts, we've kind of omitted the base. So if you saw earlier, we had like log a of b, right? So there was a base here that was important because this signifies a to the x equals b if x equals this. So this base is important because it'll kind of define what this value here is. But as you can see here, we haven't actually given a base. That's because no matter what base you choose, all of these things work the same. So all bases kind of just act equivalently, like there's no difference between them. So for example, if you have log of a multiple of two things, you can split it up. So multiplying things inside of the log corresponds to addition outside of the log. If you have log of a to a power of b, then you can just take the power outside. So powers can just leave the log freely. And then log of 1 over a is the same as minus log of a. Well, this comes from the previous part because 1 over a, log of 1 over a is log of a to the power of minus 1. And we can use this this part here. Yeah, so I think in most places you'll only ever see e because e is standard. And the reason for that is because every single log acts the same, right? So why should we all be using a different base for our logs when technically they all look and act the exact same? And so we came up with this standard base, and we call that e. So yeah, you'll stick to e, and I think that's like the next slide actually. Yeah. So and this final part actually comes from a combination of 1 and 2. So log of a on b. Well, this is a multiple of, so this is log of a times 1 on b. So you can use rule 1. So this is log of a plus log of 1 on b. And log of 1 on b we now know is minus log of b. So that's where that comes from. So as was pointed out, here's the natural log. So this is what we like to use because it's just a much nicer base. Same properties as the other logs, of course, because every single log acts the exact same. But e pops out more often, like really often, because a lot of the times you have these relations where you are adding some interest on over a period of time. And the thing is, as this goes onwards and onwards, the perpetual gained interest actually like just goes towards e. So this comes up a lot in not just economics as well. Like this comes up in nature a lot, like surprisingly a lot. So that's why we kind of like the base e for our logarithms. And so here's a graph of the log. This is kind of what it looks like. It does kind of look like it's stopping at a point, but it's weirdly enough, the log actually goes to infinity. And as you can see, it's not defined for negative numbers. That wouldn't make sense. So of course, log e of e is 1 because e to the power of 1 equals e, right? And as I said, you can't have negative numbers, and you can't have zero either. So the domain is this. The range is just everything. And it goes towards infinity really slow. One of the slowest functions to do so. And it goes to minus infinity as you go to 0, and it goes to minus infinity really quickly. So yeah, of course, log of 0 is not defined because some number to the power of x can't ever equal 0. That just doesn't happen with real numbers. Okay, so we've talked about the log. We should probably talk about its big brother, the exponential function. The exponential function we call e to the x, right? So, looks like we're not talking about e to the x yet. So I think here we're looking at just normal powers of normal exponents, but these are just like normal exponent laws, like 3 to the power of 2 times 3 to the power of 4 equals 3 to the power of 2 plus 4, which is 3 to the 6. And I'll trust that you guys know these exponent laws, and I'll just quickly go past those. Okay. So here's a nice little graph of the exponential function and the log function. So here's e to the x, the exponential. Here's log. And as you can see, they're mirrored across the line y equals x. So if you mirror the exponential function across this line, you get the log function. And similarly, like vice versa. So we actually call these inverses of each other. That's what it means. One nice thing about logarithms and exponentials is that if we have an inequality, we can actually take the exponential of everything in the inequality, and the inequality stays legit. And we can do the same with the log. We can take the log of everything in the inequality, and the signs are still valid. So for example, 3 is less than 4, and this directly also just means that log of 3 is less than log of 4. So here's an example of shifting and stretching like we did before with normal functions, but now done to the exponential. So this is your exponential graph. If you wanted to squeeze it a little bit by multiplying the x by a 3 here, so this is e to the 3x now, then you're kind of just like squishing it. And then this is e to the minus 3x, so the minus reflects it across the y-axis. Okay. So limits is now our like jumping off point into calculus. So limits are very important for calculus. So what is a limit? Okay. First of all, let's talk about what this actually means. If you have a function and you want to find its limit at some point a, what this really is the value that the function approaches from the left and the right at a. The function doesn't actually need to be valid at a, okay? The function can be whatever it wants at that exact point. It's just what it looks like it's approaching at that point that we care about. And the reason why that is so is because a lot of the times, if we have a function that has a hole somewhere, and we know what it acts like around the hole, then we can find its limit at this hole. So by looking closer and closer at this point, find its limit, and then we can actually cover the hole up and make this a nice looking function. So we can kind of like do some function like construction on these things by taking the limit, okay? And of course, a lot of functions don't actually have nice limits, so we can't always do this, but when we can, it works out nicely, and we do care about that. Not to mention that these things will be how we define derivatives later on, so it's instrumental for the rest of calculus. So here's an example of finding a limit, okay? So limit of x minus 3 on x cubed minus 27. if you just plug in x equals 3, this doesn't work, okay, because the denominator is 0. That's not possible. We can't do that. So you can't just simply plug in the value. Instead, what you do is need to factorize, and you need to cancel out terms until you are allowed to plug in the value. So as you can see here, the denominator could be simplified like this. And the nice thing about this simplification is that this x minus 3 on the top cancels with the x minus 3 on the bottom, and you're left with this. And in here, you are allowed to plug in x equals 3, because the denominator is no longer going to be 0 when you plug in x equals 3. So we do that, and we get 1 on 27. So that's our limit. So even though our function isn't actually defined at this exact point, x equals 3, we can find its limit, or like what it behaves like at this point. Some functions have weird limits where they go off to infinity or minus infinity. Some functions have no limits, like sine and cosine. So for example, the sine curve. What does this look like as x goes to infinity? Well, no matter where you go in x, it's going to look the exact same. It's going to look like a sine curve, but it's never going to look like one specific point, not one number. So we say it just doesn't have a limit because it's periodic and it's just constantly moving around. It's never like stopping at a final destination. And the one that's really nice is when f approaches a concrete value, of course, when the limit does actually happen at infinity. So what this kind of looks like in a graph is something like that. Maybe this is the number 3, so then this graph will eventually approach 3. So how do we find limits at infinity? Okay, you can kind of think of this like substituting infinity. While that doesn't really make sense, let's have a look at an example, and I think that's the best way of learning this. So if you have this polynomial divided by this polynomial, this function, and you take the limit as x goes to infinity, what we always do with these kind of problems is we divide every single term by x to the highest power. So over here, the highest power of x is x cubed for both the denominator and the numerator. So over here, we divide by x cubed. So dividing x cubed by x cubed gives us 1. Then we have minus 4x divided by x cubed gives us minus 4 on x squared. And similarly, we do it for all of the terms on the bottom. And now we take the limit as x goes to infinity. Well, 4 on x squared as x goes to infinity, 4 on a really, really large number will basically be 0, okay? So that's how we like to think of it. So this will go to 0. Similarly, 5 on x, for x being really, really large, that goes to 0. 2 on x squared will also go to 0. 3 on x cubed will also go to 0. So we're stuck with 1 on the top and 3 on the bottom, so we get 1 on 3. That's how we do those. You can also consider one-sided limits. So sometimes a graph has some weird thing going on, where if you draw it like this, it could look like this, and then on this side it'll look like this, okay? Classic example is tan. And for tan, this would be pi on 2. So how do you consider the limit at pi on 2? Well, if you do it on the left side, the limit's infinity. If you do it on the right side, the limit's minus infinity. So what's going on? Well, the reason is because there's different left and right limits here. So the left limit is when we approach the value from the left-hand side, and the right limit is when we approach the value from the right-hand side. So of course, for the left limit, we'd get infinity here. For the right limit, we'd get minus infinity for this case. Okay, and if both of these left and right limits exist, then our final limit will also exist. So great. Okay, cool. All right. This is why limits are important, because we need them to define what continuous functions are. So we say a function is continuous if we can lift if we can draw the curve without lifting our pen, okay? And this corresponds to this definition here, this more abstract definition. So if we can, so see for example this curve I drew without lifting my pen, but for a curve that kind of looks like this, I'd have to stop and then keep going to draw it. So this is not continuous and this is continuous. That's how you should probably think of this. I think the lifting your pen definition is probably better for you guys, because it saves time. You won't have to consider really annoying limits, and it's just easier, okay? Continuous functions are everywhere. All of these things are continuous. All of these things are continuous for where they're defined, and the list goes on. Okay, so all of our nice functions that we already know and love, they're all continuous. Here's some limit properties. So taking the limit of two things, you can split it up into the limit of each thing separately. Taking the limit of some function times a constant, well, you can take the constant out. The constant doesn't care about the limit. And the limit of a product is the product of the limits. But there is a but here. Only if separate limits exist. So if these separate limits are like actual values, they're not infinity, they're not minus infinity, they're not undefined. If they're actual values, then you can do this. And same goes for up here, actually. So you do need that these separate limits need to exist. You can also take the limit of a quotient, provided that the denominator doesn't go to 0, then you're allowed to do this. And if you have the limit of a power, you can take the power outside. And you can do the same for left and right hand limits. All of these things apply for left and right hand limits, and they also apply for plus or minus infinity limits. Okay, so we're ready to tackle this beast now, called calculus. Okay, and this starts with the derivative. So the derivative, what it really is the change of rate, the rate of change. So if you have a function, say if you have some sort of function of time, and this is like position of some sort of, let's say like a particle, well then the derivative, we call it ds dt. This is actually the velocity, because it's the rate of change. Okay, so this is kind of what the derivative is imitating. And you probably already know how to calculate derivatives, right? So I won't dwell on that too much. But one thing we should definitely look at is the product rule, okay? So if you have the product of two functions, then the derivative is the derivative of the first function multiplied by the second, plus the first function multiplied by the derivative of the second. And there's a useful rhyme that a lot of people know and love. Left d right, right d left. Or right d left, left d right. It doesn't matter, okay? Here's another one called the quotient rule. So when you have some function divided by another function, well then you just do this rule, okay? And where does this come from? If you don't want to remember this, you can just remember the product rule, because this is equivalent to saying f of x times 1 on g of x. And now this is a product, so we can do product rule. So f dash x, derivative of the second one is minus 1 on g of x squared times g dash x, right? And then you also have to do the plus the other part, and it ends up looking exactly like this. So that's kind of where it comes from. So we can also do something called chain rule, where we have some function inside of a larger function. So it'll look like f of g of x, for example. Then when we differentiate, we need to take the derivative of the inside function and multiply it by just the function, the derivative of the outside function. There should be a derivative there. Okay. So for example, if I do ln of x squared, I think someone in the chat was asking about chain rule today, so I think this is useful to go through. So derivative of the inside function, well, the inside function is x squared. Okay, so we need to take its derivative, x squared. We multiply it by the derivative of ln of x squared, but we kind of ignore the fact that the x squared is there now, so the derivative will look like this, and the inside is 1 on x squared, which is 2 on x. Okay. So the derivative can tell us a lot about a graph, actually. So if we draw a graph, right? If at a point in a graph, so we have a graph that looks like this, and this is point A. The derivative, if it's positive, that means the velocity is positive, and that means the graph is increasing. Okay, it really does just mirror the idea of velocity. And if we take the graph over here, and we're going here, then at a point B here, the derivative would be less than 0, and that just means the graph is decreasing at that point. Then at a point like here, at 0, the derivative would be exactly 0, and that means that the graph is stationary, and it could be turning. So as you can see, it is actually turning here, it's changing direction. And we can also use the second derivative to work out things. So for example, with so if the second derivative, so the second derivative is just taking the derivative again. If it's greater than 0, that means the graph is concave up. Okay, means it looks like a smiley face. If it's less than 0, that means the graph is concave down, so it looks like a frown. And if it's exactly 0, then there's no concavity. That means it could look like oh, that's odd, my pen's not working. Alright, whatever. If it's exactly 0, then it would look like it's stationary but not changing direction. Okay, so derivatives have some special properties we can take advantage of. Okay, see if this works. Oh, okay, works now. So the first property is that derivative of the exponential function is really nice. Logarithm function derivative is really nice. All of these are really nice. Okay, so I'll leave this slide up to you. So this can be like a nice little cheat sheet if you want to use it. But yeah. And so we can actually use derivatives of functions to sketch things really well, because as you just saw, it gives us some nice information about a function. We know when it's turning around, we know when it's smiling, when it's sad, we know when it's increasing, we know when it's decreasing. So it's really useful to be able to draw a function. So whenever we're drawing a function, we generally want to follow these rules. First of all, we need to know where the function is defined. Okay, and if there's any spots where the function isn't allowed to be defined. Rule number 2 is not that important, and honestly, I don't really do this often. So I don't know how often you need to really do this one, but if you know it's an odd or even function, it kind of helps. But again, I personally don't think it's that useful. Number 3, finding x and y intercepts. So if you have a graph that looks like this is a y-intercept, this is an x-intercept, so it just helps to be able to connect the dots, you know. Finding vertical asymptotes. So if your graph isn't defined somewhere, so for example tan, knowing what tan, where tan approaches infinity is really helpful, because this is pi on 2, right? So we can kind of use this as like a guide when we're drawing tan. So knowing these asymptotes are really cool. You can also find horizontal asymptotes. So for example, if you have a function that is doing this, then knowing where it's going towards is kind of helpful. First derivative, so this is where the derivatives come into play. So knowing its derivatives, its turning points, which way it's going is really helpful. For example, if you have something that looks like this, then knowing where exactly these two turning points are really helpful, because we can kind of connect the dots between them and these x and y intercepts as well. Okay, so we have a lot of points to work with at that point, and it just falls out really nicely. And of course, like if you have periodicity, then what happens is you only need to draw the function for one period, and then you can just copy it for all the other periods. Okay, oh, that was a period. Whoops. Here you go. Yeah. Okay, that leads us to an important theorem that kind of may sound obvious to some. If you have a continuous function on some interval, so like this, then at some point on this interval it has a maximum value, and also it has a minimum value. So for example, for this one, the maximum happens to be here and the minimum happens to be here, but that's not always the case. For example, if I draw something that looks like this, then here's the maximum value and here's the minimum value. Okay. So maximum and minima can be found at the endpoints or at critical points, okay? So this is for a function in general, not on an interval. If you have some function and it's defined on like, if its domain is like a, b, some interval, and it goes into like maybe its range is like all of the real numbers, then you can check the endpoints to try and find maximum values and minimum values, or you can find critical points. Critical points are where f dash of x is 0, or f of x is like plus or minus infinity. So you want to check all of these kind of values, okay, to find your critical points. So on open intervals, you might not actually have maximum and minima at the endpoints, because it kind of gets weird around the endpoints with infinities. But inside of the open interval, you'll still have some turning points to work with. So if this is an open interval, then you can still find these turning points, okay? It's not too much of a worry. So, okay, in the next part, we actually want to use these to model things. So, one way we can model something is we can model it by how much it changes, okay? So if it changes proportional to its own growth size, you can see this with like species. So some sort of animal, as it populates more, the more of its type there are, the more it's going to populate. Okay, so it's what we say is that its rate of growth is proportional to its population size, and this is how we denote it. So here's an example using radioactive decay as well. So with radioactive decay, the rate it decays at is proportional to its size. So K can be positive or negative, so it could be going upwards or downwards, okay? Either way. And if we solve this equation, we get this out in the end, y equals a times e to the kt. So as you can see here, e is back, right? So really weird number there. Here's one example of using this to model something, okay? So if you have a population that's growing exponentially, oh, sorry, this one might not be growing exponentially, okay? So you have a population of trout, 100 trout, okay? And within 1 year, that number grows by like twice. And what happens is that the population of the trout might grow exponentially if the pond is large, but the growth rate is going to get smaller and smaller as the population increases. Okay, so you can model this like this, and this was given in the paper, by the way. So this is from the 2018 paper. So they gave you this equation to model your growth rate, and what they've asked you is to do these things. First, they asked you to estimate the population after 10 years. So, okay, let's do that. So, we know that our solution is something that looks like this, because this is exponential, okay? Go back up here. So the thing is, it could be exponential, or it could not be, depending on how big it is. So initial population is 100. So that means that a p of 0 is 100, okay? So at time equals 0, we need to have 100 trout. So that's why we find that a equals 100. So our p of t can be rewritten as 100 e to the kt. After a year, we get double 100, okay? That means that p of 1 equals 200. And so solving this, so we have 200 equals 100 e to the k, and we can solve this just using log laws, so k equals log of 2. And so we can rewrite our p of t equation like this. It looks nice now without any unknown coefficients. We can simplify this further because e to the ln2 is just 2. So that's where this comes from. So as t goes to infinity, our population is going to go to infinity, okay? Because as you increase the power of 2, it just gets larger and larger. And after 10 years, we get this many. And I think, yeah, we only included part A in this from this past paper question. But I think if you go back and look at the past paper questions, part B and part C were pretty interesting as well. We can use trig functions to model as well. So for example here, when you have something that oscillates, you can always model it using a trig function. Here we're doing volume of air in a person's lung. So of course, like as you breathe in, you're going to get lots of air. As you breathe out, you're expending air. As you breathe in, you're getting lots of air, etc., etc. So it is oscillating like a trig function. Okay. So this question asks us to find the maximum and minimum volume of air. Okay, well, we look up here at the volume of air. We see there's a cos here. Well, the thing is, cos is always bounded above and below by -1 and 1. So that means 0.18 times cos is bounded below and above by 0.18 and -0.18. And we also need to add 0.3 to this. So if we plus 0.3, then we need to do plus 0.3 here and plus 0.3 here. And so the minimum will become 0.12, maximum will become 0.48. So that's the most amount of air that the lung can have under this model. I'm not sure how accurate that is to actual lungs. What past paper was this from? This is from 2019. Okay, so reasonably recent. So this next part asks, when is the volume changing at a rate of 1.728? Well, to find the change, you take the derivative, okay? So we did that here. And we need to equate it to 1.728 and find the time because it's asking when. Okay, so rearrange this. So they chose 1.728 nicely for us because it cancels. So we get sine of 9.6t equals -1. And we know when sine of what equals -1. Okay, so sine of 3 pi on 2 equals -1. So that means that the inside here needs to be equal to 3 pi on 2. So we take 9.6t equated to 3 pi on 2. So t is approximately that number there. Okay, so another very useful trick in modeling is the line of best fit. This gets harder and harder as you have more data. Usually you can always get some sort of program to make a line of best fit for you once you plot your data. But it's useful to know how exactly this works so you can do this quickly and like know how the data is kind of acting as you do whatever experiment you're doing, I guess. So let's see how this line of best fit works. So given some sort of table of values, we want to find the line of best fit. So if we have some P and some Q, how do we find a line of best fit? Well, hang on. Okay, yeah, it's coming. So what we can do is, I think there was a mistake in this slide. 1 second. Okay, yeah, no, all good. So what's going on here is that they want us to measure Q, and Q is given by this log. And for the first part in this 2019 question, they're asking us to make a table of T versus Q. So we plot T here, plot Q here. So T equals 1, P is 20. So we plug in 20 into the Q formula, and we get this out. When T equals 2, P is 26. We plug 26 into the Q formula, we get that out, etc., etc. And we just keep doing that for all the values of T. And so we have this table of values. Okay. So now it's asking us, in part B of this question, to find the least squares line of best fit, Q equals MT plus B. Well, we have a table of values for Q now. So from the table of values, we can say this. If Q is MT plus B, then M times 1 plus B has to be the first value in the table. M times 2 plus B has to be the second value, and so on. Sorry. And so what you have here is you have some matrix of equations, and you can equate them to the right-hand side, or the left-hand side in this case. So that's exactly what we do. We put all this into a matrix, okay? So M plus B is, so we have 1M and 1B. 2M plus B, we have 2M's and 1B, and so on. And then this side is just resulting values. What we do next in the line of best fit, like least squares method, is we multiply both sides by the transpose of this matrix. Okay, so we do that to both sides. So here's the transpose here on the left side and then on the right side. And multiplying through by the transpose, on the left side we get this. That's just by doing matrix multiplication. Same thing over here, just matrix multiplication. So now we need to multiply both sides by the inverse of this thing. So that's what we do here. We multiply by the inverse. And of course we need to do that on the right-hand side as well. And this isolates the MB. And so now we know that M is this and B is this. Plug those into our Q formula, and there you go. We have a nice approximate line of best fit for Q. Okay, here's another line of best fit example. I'm going to quickly skip through the next few because we are a bit short on time. So we can also do it with quadratics. The thing with quadratics is you'll have three variables, and then you'll have to do your matrices will have 3 columns instead of just 2. You can also do exponential. So when we have like y equals a times e to the kx, what we do is we take the log, so the natural log of both sides, and what we get is ln y equals, well, we have a k here, times ln of e to the x plus log of a. And this is the same as kx plus log of a. And so we rewrite it like this. So y equals log of small y, k is the same, x is the same, and this b now is the log of a from before. And now we have a linear equation, and we can go back to doing a line of best fit. Okay, so here's some 3D algebra, because why not? This is very useful when modeling physical scenarios. So for example, here we have this equation for a plane, and what this looks like is just some sheet of whatever material, I guess. This is how you would write it mathematically. So a, b, and c can be any numbers, and they can be 0 if you want. And you can find where they intersect the x and y axes and the z axes as well, because now we're working in 3 dimensions. Okay, so we have one axis here, we have another axis here, we have a third axis going up. We can find distances, so the distance still works the same as it would do in 2D. So you just find first term minus second term squared plus our first term minus first term squared, plus second term minus second term squared, plus third term minus third term squared, and you take the square root, of course. So it's technically like Pythagoras' theorem, but for 3D. You can find midpoints of points. So you just take the coordinates and you divide by 2. That's it. Pretty simple. There's intersections, of course. So two planes can intersect in a plane, a line, or not at all. So if I draw two planes, if they intersect in a plane, that means that they're the exact same plane, right? So if I kind of draw it out here. So these two planes are the exact same, so they're intersecting in a plane. Planes can also intersect in a line. So if I have a plane that kind of looks like this, I have another plane that kind of looks like, let's use black. Then their intersection point is right there, right? So it's a line, as you can see. Or they can not intersect at all. You can have a plane like this. You can have another plane like this, and they're never touching. Right, cool. So here's some more information about intersection of planes. Okay, I won't go into it too much. This part is really important, so this is what I wanted to speak towards. So linear equations is really important. So this talks about row echelon form, okay? The row echelon form is when we have a matrix where you can have some term here, you can have some term here, some term here, but these all need to be 0. Maybe like -1. Row echelon form because what's happening here is that the first non-zero number in each row is in a column to the row above it. So here the first non-zero term is 1. Here the first non-zero term is 2, which is right next to this column. The first non-zero term here is 3, which is right next to this column, and so on, so on. So this is what we call row echelon form. This is really really useful for solving equations. Okay, so if we have like 1, 2, 3, 4, xy, and we want to find xy, and if it equals like 5 minus 2, then we can consider 1, 2, 3, 4 with this minus 2, 5 on the side, and we can turn this into row echelon form, and it will solve for x and y. How do we do that? Well, we can swap rows if we want. We can multiply one row to another row. We can multiply and divide any row with a constant as well. So using some combination of these three operations, we can turn our matrix into row echelon form. And I think there's an example that would be very useful to go through. Yeah, so there's an example coming up. So here's like a quick like step-by-step guide. Okay, so you put your system into this form ax equals b, convert it into augmented form, then you just do the Gaussian elimination with row reduction, and you just keep using pivot points, okay? And I'm pretty sure you've seen this in lectures already, but we'll go through an example. And then, of course, you need to perform back substitution. So here's a really packed example from 2019. So it gives you a restaurant with 3 types of salads, healthy, green, and tasty. And it's to do with the ingredients involved in these. Okay, so healthy has 1 pack of dried fruit, 2 mixed vegetables, and 2 meats. The green has 1 dried fruit, 5 vegetables, 0 meats. Tasty 2 dried fruits, 1 veggies, and 6 meats. And you have a total of 126 fruit, 198 vegetables, and 288 meats. And you want to know exactly how many of X, Y, and Z you can make. So X, Y, and Z are the servings of each of these salads. So what we really have here is 3 different equations. So the servings need to add up. Okay, so each serve of healthy contains 1 dried fruit. So that's why there's 1 of X, right? And each serve of green contains 1 dried fruit, and each serve of tasty contains 2 dried fruit. So the total of the dried fruits needs to add up to the total amount of dried fruit stock we have, which is 126. And you do the same with the other 2 ingredients here. Okay, so for example, the first one, which was the, what's it called? Healthy one. So that the healthy one has 2 meats, the green one has 0 meats, and the tasty one has 6 meats, and it needs to add up to a total meat stock. So we can turn this into a matrix, like so. And now we just perform these row operations that we learned earlier. So for example here, what we're doing is we're taking row 3, and we're doing row 3, and we're taking away 2 of row 1. So how do we do this? Well, we take this 2, and we multiply it by 2 times this 1. We take this 0, and we take away 2 times this 1. And we take this 6, and we take away 2 times this 2. And that gives us our new 3 values here. And also we have to do this on the right-hand side. So 288 minus 2 times this 126. And we get that. And then we're also doing this for row 2. We're doing row 2 minus 2 times row 1. And we get these values. And on the right-hand side as well. And we're not touching row 1. Row 1 can stay as is. And next, to go from here to here, I'll erase some of these lines so we can see clearer. To go from here to here, we're doing row 3 minus 2 on 3 times row 1. The reason why we chose this is because we want to get rid of this minus 2. And so when we do so, we get a 0 here. And similarly, we get a 0 here. And we actually get a 0 there as well. So now we do some back substituting. So what's going on here? Well, row 3 is not telling us any information because it's all zeros, but row 2 we can actually learn from. What row 2 is saying is that 3 of y minus 3 of z equals minus 54, okay? We don't know what z is, and we can't know what z is because row 3 is informationless. So we just make z a parameter. We say z equals t. Then what we have is 3y equals 3t minus 54. And now we just divide everything by 3. And hence we get this equation for y. Doing the same for row 1 will give us this equation for x. Okay? And so what we have now is we have an equation for x in terms of t, for y in terms of t, and z is just t itself. And we can rewrite it to look like this. Okay. Great. So usually we do want to keep these x, y, and z positive, right? Because it'll be kind of weird if the number of the number of salads we were making was negative. That doesn't really make sense. So that means that like this t minus 18, for example, has to be greater than 0 or equal to 0. So that means t has to be at least 18. Okay, I won't go too much into that, but that's it for my half. Okay, I think I went 8 minutes over time. But Donald will take over now for the second half, starting with matrix multiplications. But thank you, everyone. And I'll stop streaming now. Thank you, everyone. I'll stop streaming.
Hello, hello. Can people hear me? Just testing real quick. Hello, hello. Can people hear me? Okay, looks like it works. So, I guess we'll just jump straight into it. Let me see if Abdullah has anything to say. I'm up. Okay. Guess we'll start, guys. So, welcome to the second half of your Math1031 revision seminar. We're going to be covering matrix transformations, partial differentiation, all the differential equations and all that stuff as well. So hopefully I don't get any technical issues because my internet is a little sometimes. So if there is like a problem, just let me know in the chat because I will have it open. All right. So matrix transformations. What is a matrix transformation? So we can interpret a 2x2 matrix transformation as shifting the unit vectors I and j by each column of the 2x2 matrix. And now every vector under this new transformation will now be expressed in terms of these new unit vectors. So pretty much before, what would happen is we would have our unit vectors I hat, and j hat here, which just represents 1, 0 and 0, 1, right? And every vector would be expressed in terms of these two vectors. So for example, if I had a vector 3, 2, all we're doing is multiplying I by 3. So we're moving 3 across, and then we're moving 2 up, all right? And that's all we're doing, okay? We're multiplying our standard basis vectors. And that's the reason why when we multiply a vector, for example, 7, 6 by 1, 0, 0, 1, which is the identity matrix, everything stays the same, yeah? It still becomes 7, 6. However, now when we apply a matrix transformation, if it's like, 7, 4 and, 1, 2 or something, what we're actually doing is we're going to our plane. We're looking at 7, 4, I don't know where 7, 4 is. It's like here. And 1, 2 is going to be like here, actually. So what's going to happen is you're actually going to be measuring all your new vectors in terms of shifting these vectors like that and shifting across like that, right? It's going to be in terms of these vectors. But yeah, that's pretty much all we're doing. I like to envisage it as just shifting like the grid lines on your Cartesian plane. And yeah, and the resulting vector after applying a transformation is called the image of the vector, sorry. So apply the transformation of 3, -2, and 2, 1 onto the vectors 5, 7, and 1, 2. What are their images? So when you're applying transformations, all you need to do is do normal matrix multiplication. So in this situation, what we're going to do is we're going to get 3, 2, -2, 1. And we're just going to do, matrix multiplication. I'm sure you guys are super familiar with this. The 5, we sort of like do a dot product with these vectors here. So 5 goes to 3, 15 plus 7 times 2, 7 times 2. And then this 5 goes to -2, so -10 plus 7 like so. Blah, blah, blah. And we'll see that indeed we will get 29 and -3. It's just matrix multiplication. All right. And now we're going to also do it on 1, 2. So as you can see, 1, if we do the calculation, 1 times 3 is 3, plus 4 is going to be 7. And then 1 times -2 is -2, plus 2 is 0, because -2 plus 2 is 0. So yeah, that's pretty much it for your images of your transformation. And the thing about it is, when you apply a transformation onto vectors, they will form different shapes, right? For example, if you have a square and you shift all its vertices, this is going to create a new square. And that new square is going to be squished or translated, and it's going to have like a different area. It's going to have different properties. So let's take a look at an example of a question. A right-angled triangle T has vertices at 1, 1, 2, 1, and 2, 4. When T is transformed by the matrix, the image is T dash Find the coordinates of the vertices of t dash and describe the transformation represented by P. So, what do we do in this question? First, I'm pretty sure when I looked at your past papers, they all love to ask you to graph it out. So we'll graph it out for now. We have 1, 1, which is here. Usually you would do this a little bit more to scale with a ruler and everything, but I do not have a ruler on me. 2, 1, so it's going to be across and it's going to be on the same level. And finally we have 2, 4, so it's going to be up here actually. 2, 4, and that's going to be our triangle, like so. Right angle triangle. And they're asking you, what are the coordinates of the transformations when you apply P onto it? So this question is fairly straightforward, and the transformation matrix is actually very simple. It's just 0, 1, 1, 0, right? So it looks like the identity matrix, but it isn't. It's everything flipped around. And let's try it, right? 1, 1, 0, 1, 1, 0 is going to be multiplied to 1, 1. Let's see what happens. This goes to, all right, so this is just going to be 1, 1, right? So we're going to plot out 1, 1 here. It's the same point. Let's try and do 0, 1, 1, 0 for a different vertices. So 2, 1. So 2 goes to 0, 1 goes to 1, so it's going to be 1. 2 goes to 1 and 1 goes to 0, so it's 2. It's going to be 1, 2. So where's 1, 2? 1, 2. It's going to be, it's actually going to be up here actually. 1, 2. And then we're going to look at our final transformation. What is it? 2, 4. That's going to be, let's see, 4, 2. So as you can see, if you haven't noticed already, basically what this transformation does is flips the x and y coordinates. We have 1, 1, 1, 1, 2, 1 becomes 1, 2, and 2, 4 becomes 4, 2. So in here we're going to look for 4, 2, which is actually going to be about here. And here's going to be our new triangle, right? And is that correct? Yeah, it should be correct. It might be a little off scale, but whatever. Yeah, okay, that looks right. So now you have to describe the transformation represented by P. And in this case, you have to realize what the actual transformation is. And when you swap the x and y coordinates, the transformation happens to be our reflection across the line y equals to x. So you have a line y equals to x here, and what you're doing is you're actually like flipping it across, right? So it's actually gonna look like sort of like this, and the line y equals to x comes across the middle. But I'm not very good at drawing that. You should be able to determine the transformation, and sometimes there's many different transformations. For example, rotations and blah 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 blah. The best way is to probably either graph it out or take a look at like what gets transformed to what. Alrighty, moving on. Markov processes. So what is a Markov process? A Markov process is one where the probability of the next event is only dependent on the state of the future event, on the state of the previous event. And by previous, we mean the most recent previous one. And when predicting future states in Markov processes, there is no difference between knowing the entire history of the process and just knowing the state achieved currently. So, I mean, the one that's most commonly used to show a Markov process is there a way to predict how the shape will change just by looking at the transformation matrix? Is the question in the chat. Not necessarily. What you can do is look at the vectors, like these vectors, and see what sort of new vectors they map to. But generally, it's pretty hard to predict what it is unless it's a rotation matrix, which you can just, I guess, just know what it is. And for example, something like this, right? Like this is going to be a flip because it looks like the identity matrix where it's flipped. But yeah, there's not really a good way to look. You just got to draw it out. Alrighty. Oh, but you can, if you find the determinant, you can also find how the area changes. If they're dealing with areas, that really relates to determinants. But yeah. Okay, back to Markov processes. So for example, we're playing scissors, paper, rock. And sorry if I'm rushing, by the way, because there's a lot of stuff to go through. So we have scissors, paper, rock. For example, once you throw scissors, there's a chance, like if I throw scissors, I have a 1/3 chance of throwing, I don't know, paper or something. And if I'm throwing, and there's like a 1, 2 on 3 chance to throw rock. And if I throw paper, there's another chance to throw blah, blah, blah. So basically, what I throw depends on what I threw before. And that's an example of a Markov process. Because if I have a series of like rock, paper, paper, scissors, rock, knowing that I threw these doesn't help me predict what I'm going to throw next. All I need to know is I threw rock, I'm going to go to the law, and I'm going to say, oh, he's got this chance to throw, paper or something. So these, I'm not saying they're useless, but they're useless for predicting the next state. All right? And since the rules for transitioning to the next state is fixed, we can describe each state-to-state transition with a matrix, size depending on the problem, okay? So we can put everything in a matrix and apply a matrix transformation. Thus, we can represent our current state by using a single column vector, also of variable size, and to find the next state, we multiply our column vector and the transition matrix together. Long story short, we have our states. For example, scissors, paper, rock. We chuck everything inside a matrix like this. The size depends on like how many conditions are given. And your state, for example, rock, paper, scissors. This is going to be the current state. For example, if I throw paper, the state is probably going to be represented as 0, 1, 0. And then etc., right? Or actually, it's going to be in probability. So this might be 2 on 3. This might be like 1 on 3. The chances of throwing blah, blah, blah next. But yeah, that's pretty much how Markov processes work. This is so be very careful, right? When you're checking your solutions, each column in a transition matrix must sum to 1. So each column like this. And to find the previous state to the current one, we simply multiply the inverse of the transition matrix. So in order to move from a state to another, we multiply the thing. And if we want to move backwards, so for example, move from rock back to scissors, we do the inverse of t, which we described, I think, before in our matrix algebra section. Okay, so long-term and steady-state solutions, blah, blah, blah. Basically, long-term solutions, when you apply the transition matrix like 50 times, okay, not 50 times, like infinity times. The moment where the solution, which doesn't change after repeated applications, is called a long-term solution, and it's a steady-state solution. One where repeated applications of the transition matrix will not do anything. So everything will just eventually reach a steady state. And not every Markov process, has this condition. Some just alternate back and forth, but a lot of them definitely do. Okay. Oops, that's a little bit bugged. So here's an example. A fast food restaurant owner is considering the effect on his business, McDonald's, by a new fast food restaurant that opened down the road, KFC. Currently, McDonald's has an 80% of the market, and KFC has 20%. After analysis over the past week, they discovered the probabilities for the customers switching the fast food restaurant they stop at each week. So basically, every single week, these guys have market shares, and depending on which stop they stop at, there's a chance they stay or they switch to KFC. So if they stop at McDonald's, there's a 0.75% chance they stay, 0.75 chance, and a 25% chance to switch to KFC. If they stop at KFC, there's a 0.45 chance they stay at KFC and a 0.55 chance to switch at McDonald's. What is the expected market share for McDonald's and KFC after another 2 weeks have passed? What is the long run prediction for their market shares? So the expected market share after 2 weeks, hopefully you guys should already realize that, this is just 2 applications of the transition matrix. So let's quickly form the transition matrix here. What is it? Okay, so if they stop at McDonald's, there's a 0.75 chance they stay. So 0.75 and 0.25 chance they switch to KFC. So 0.25 goes here. And over here, there's a 0.45 chance they stay at KFC and a 0.55 chance to switch to McDonald's. So in this case, be very careful. The solution is not 0.45, 0.55. Instead, it's actually this flipped around, okay? 0.55, 0.45. And I'll explain why in a moment. So basically, one sanity check you can do is just see, oh look, the columns add up to 1. Therefore, there is a pretty good chance our transition matrix is somewhat correct, okay? And now let's take a look at why the ordering matters, all right? So what is our state? 80% of the market share, and KFC is 20%. So we'll make this 0.8, and this is 0.2. This represents McDonald's, this represents KFC, all right? So what we're doing now is we're saying, we're going to be doing a matrix multiplication. So 0.8, I'll do this in a different color actually. 0.8 is going to go to 0.75. 0.2 is going to go to 0.55. And that's going to come into our very first term, added together, yeah? And this represents McDonald's, because what this outputs is another like state column, sorry, state vector, and the very first row represents McDonald's. So this represents McDonald's. So what's happening is we're saying 0.8%, 0.80% of McDonald's has a 75% chance of stay. And the 0.2 of KFC has a 0.55 to stay at McDonald's. So basically, the problem is 0.55 is actually a McDonald's probability, which means we must put it in the McDonald's row. All right. And look, I'm not going to do the calculations because I've already pre-calculated it when like writing this question. The first state is going to be, after doing the calculations, it's 0.71 and 0.29. And then what you're going to do is you're going to apply the state transition matrix again onto it. And for example, you basically replace this vector with this vector, and you do it again, and you'll get 0.692 and 0.308. And that's going to be your after 2 weeks. So as we can see, McDonald's lost a little bit of share because it was 80% before, now it's 69%, and KFC rose to 30%. So what is the long run prediction for their market shares? So basically, long run means TV equals to V. When you apply the transition matrix onto the vector stays the same. All right, that's all it means. Nothing changes. So how do we do this? What we do is we let V equals to x1, x2, and we solve for x1, x2. So the transition matrix is going to be, let's see, it's going to be 0.75, 0.55, 0.25, 0.45, like so. And we're going to have x1 and x2 here. We're going to apply on, so 0.75 x1 plus 0.55 x2. Oops, this is some horrendous handwriting. Very sorry, guys. Equals to, and we wanted to say the same, right? So this is going to equal to x1. And then over here, 0.25 x1 plus 0.45 x2 equals to x2. And these are our simultaneous equations that we need to solve. As we can see, we have two variables, x1, x2, and two equations, which means we can solve it, all right? And to help us, we also have one more very useful equation, x1 plus x2 equals to 1, because the column must add up to 100, basically. So 1. And we're going to solve this simultaneous equation. I'm not sure if I should solve it because it is very time consuming, but what we do is basically we say, oh, you know, x1 equals to actually we'll do x1 equals to 1 minus x2, and then we go over here and we do 0.75 1 minus x2, oh my goodness, x2 plus 0.55 x2 plus 1 minus x2. This is from the first equation, by the way, and we basically isolate everything, find x2, find x1, and then solve it. It's just a simultaneous equation, okay guys? Hopefully that isn't too rough for you guys. And once you find x2, you sub it into this equation here, and you find what x1 is. So x2, x1. The answers I got was x1, x2 equals to 0.6. Oops. You guys should definitely attempt this when you guys have time, because it's good practice. 0.3125 and this is your steady state solution. So what you can do after this is basically apply the transition matrix on this again, and you'll see that it actually stays the same and nothing will change. Okay, but that's pretty much it for this question. Not really that much to say. If you're confused, just ask me a question in the chat. All right, difference equations. So, okay, what are they? A difference equation is where terms of a sequence are defined recursively, i.e. in terms of previous values. For example, yn plus 1 equals to 6yn plus 3. Clearly, look, the n plus 1 term is defined in terms of its previous term, okay? And that's a difference equation. And they're also called recurrence relations as well. So there's multiple names. If you're like searching up how to do them, maybe search up how to like solve a recurrence relation instead of searching up how to solve a difference equation. Anyways, the order of a difference equation is a difference between the highest subscript and the lowest. Basically, the one in the previous slide has an order of 1 because n plus 1 minus the lowest, which is n, equals to 1, all right, because these cancel out. A homogeneous difference equation is one where there's no constant. Okay, so if you move all the terms with subscripts to one side and the other will be 0, a non-homogeneous equation is where there is a constant on the side without the subscripts. So over here, this one is a non-homogeneous because when you move everything to one side, yn plus 1 minus 6yn, there's going to be a constant on the right-hand side, and therefore it's non-homogeneous. If this was 0, then it would be homogeneous. A first-order homogeneous difference equation is just a geometric progression. So, first order, if this was 0, we're saying yn plus 1 equals to 6yn. So it's just the previous term multiplied by 6. All right, that's a geometric progression where, like, I mean, you guys should already know what a geometric progression is, but it's just where every term differs by a like a multiplication factor, I guess. And this course is on first and second order homogeneous difference equations. You will not be dealing with constant values. Let me know if I'm wrong, by the way, but I think that's the case. So, for second order difference equations, given the equation axn plus bxn minus 1 minus cxn minus 2, so this is actually a second order difference equation, we can obtain the auxiliary equation, this. To get the auxiliary equation, basically replace xn, or the highest one, with lambda squared, and then xn minus 1 with lambda, and then the last one will just not have a lambda there at all. And this is going to be a quadratic, all right? And then what you need to do is solve the quadratic for lambda 1 and lambda 2. And your general solution will now be a, lambda 1 to the power of n, and b, lambda 2 to the power of n, and where a and b are just are constants. So you don't actually know what a and b are unless you're given initial conditions. But otherwise, it's just solving a quadratic and then subbing everything into just this general solution. As for first order, we pretty much already know that xn equals to can, where the equation is this. So obviously we'll do some examples to take a look at what's going on here. So the first one is clearly a first order differential equation, and it's homogeneous as well. So we're going to see xn equals to negative 3 xn minus 1. Oh, sorry, it's just 3 xn minus 1. And it's saying that every term in this series is multiplied by 3. The starting term is 2. So it's pretty obvious that since the starting term is 2, the next term is going to be 2 times 3, which is going to be 6. And it's going to be 18. And it's going to be, you know, whatever, 18 times 3. What is the solution to this? Well, xn equals to ca to the power of n. And yeah, there's not really that much to say. A in this situation is 3. So xn actually equals to c3 to the power of n. And they even give you an initial condition, x1 equals to 2. So x1 is going to be 2, and then you sub in 1 to n, so c times 3. So therefore c equals to 2 on 3, and therefore xn equals to 2 on 3, 2 on 3 times 3 to the power of n. But since it's divided by 3, we can subtract 1 here. And that's it. This is going to be our solution. And the beauty about this solution is that if I want the 100th term, I can just sub 100 into this equation, and I'll get the 100th term. Whereas with this, the recurrence relation or the difference equation, I have to sub in 1, 2, 3, 4 all the way up to 100 to calculate what it is. But this one, you can just jump straight to the nth term. All right, now for the second order difference equation, we have this. So let's convert it to a quadratic. Lambda squared minus 5 lambda plus 6 equals to 0. How amazing. Oops, that looks like a D. 0. And then we're going to solve this quadratic. So it's going to be lambda minus 3, lambda minus 2. And therefore lambda is going to be equal to 3, 2. And what we're going to do now is go to our general solution here. And then, wait a second, is there? Okay. Go to the general solution and sub it in. So xn equals to a lambda, okay, so 3 to the power of n plus b 2 to the power of n. And that's our solution, okay? And if they give you initial conditions like this, you have to sub them in and you have to solve simultaneously. So x0 is going to be 1, so it's going to be a plus b, because 3 is going to be to the power of 0 and 2 is going to be to the power of 0. X1 equals to 0, so 0 equals to a times 3 to the power of 1 plus b times 3, 2 to the power of 1. And then you solve simultaneously. So for example, a equals to 1 minus b, so 0 equals to 3, 1 minus b plus 2b. And solving, we're going to get 3 minus 3b plus 2b, and therefore b is going to equal to 3, I believe. Let's see. Yeah, it's equal to 3. And subbing it back in, a is going to be negative 2. So we're going to have our final equation as xn equals to negative 2 times 3 to the power of n plus 3 times 2 to the power of n. All right, and that's pretty much it for this question. And that's pretty much it for solving general difference equations. A lot of the times they will ask you, like, they give you a scenario like there is 5 chickens and these chickens, you know, do all this stuff, but just convert it to a simple difference equation and solve it, or a differential equation, depending on what the question asks. All right, so now we're going on to differentiation revisited. Implicit differentiation. So this is used to differentiate messy equations that we cannot use our traditional methods on. For example, this. Like, this is going to be, it's possible, but it's a big trek to find y in terms of like x. So, you know, fx, and then differentiate it. What you want to do is use implicit differentiation. So the formula is here, all right? And if we analyze this formula carefully, it's saying dfy on dx equals to dfy on dy times dy on dx. So what it's saying is, when you try to differentiate a function of y in terms of x, you clearly can't. Like, if I want to go y squared, differentiate this in terms of x, there's no x there, so you can't do it. So what you have to do is use the chain rule, differentiate it in terms of y. See, this is a dy, so we can do it, and then multiply dy on dx to it. So we don't actually know what dy on dx is, we just multiply to it. So for example, we have x squared plus 3x plus 2y plus 3y equals 0. We'll implicitly differentiate that. So we differentiate it in terms of x. So we have 2x, because that's just normal, plus 3, that's just normal. And then now we try to differentiate 2y squared. So what we do is differentiate it normally, treat y as just a variable, so it's 4y. And then what you do is, since you differentiated y, you multiply dy on dx to it. And then plus 3 times dy on dx, because we multiplied it by, we basically, you know, multiplied it by, we differentiated a y. All right, and this is described here. If we move all the variables to one side, if blah, 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 differentiate the x normally, and every time you differentiate y, multiply by dy on dx. Thus, and then express everything in terms of dy on dx. So just factorize dy on dx out. 4y plus 3 equals to negative 2x plus 3, and then 4y plus 3, and then divide it, 4y plus 3. And bam, we've done it. We found dy and dx for this function here. And you'll notice that, sorry, it's not a function, it's a relation. But for this thing here, it actually requires x and y. So you actually need a whole point. You can't just say, what is the value of this at x equals to 1? It's what is the value of this at x equals to 1, y equals to 2. And it's going to give you the gradient at that point. And usually it's like in circles, right? Just giving x equals to 1, you don't know which one they're referring to, this tangent or this tangent, right? And that's why you have to specify the y as well. It's used to differentiate functions, sorry, non-functions, so when there's two y values for a single x. All right, parametric differentiation. When x and y are not in terms of each other, but a parameter, e.g. t. So in this case, we would have something like, x equals to ft, y equals to gt. We can use parametric differentiation to find dy and dx by expressing it as dy and dx equals to dy and dt, dx on dt. So basically what it's saying is, dy, the dt's will cancel out and you'll just be left with dy and dx. And we can work these ones out, but it's going to be hard to do this in one go, right? So you want to create these two first. So we'll do an example over here. While it's fresh in our minds, let's do the parametric first. So dy and dx, actually no, we'll do the implicit first. Use implicit differentiation to find dy and dx for x cubed y equals to 27 and the gradient at the point 3,1. So this one trips a lot of people up when they're first learning how to do implicit differentiation, because this is not the x and y's aren't separated, right? They're combined. And what you have to do is use the product rule and treat this as a different function. So I hope you guys are familiar with the product rule, but what you do is you differentiate this, multiply this, and add it to differentiate this, and then multiply by this. So differentiate x cubed, 3x squared times y. Nothing happens because we didn't differentiate y. Plus, now what you have to do is differentiate y, which is 1, times x cubed. And then since we differentiated a y, we multiply it by dy on dx. And that's right hand side is going to be 0. Like so. And then what we do is we just isolate for dy and dx. So we're going to have negative 3x squared y on x cubed, like so. And then this will cancel out as well. So subbing in the point, 3,1, 3 cancels out there, so it's just going to be negative 1 at 3,1. And that's going to be your answer. Okay, very cool. Very cool. And that's pretty much it for this example of implicit differentiation. Now that you obtain the gradient, you can, find the tangent and all that shenanigans. So yeah. All right. Find dy and dx when x equals to t cubed minus t and y equals to 4 minus t squared. This is just implicit differentiation, not exactly too difficult. Dy and dt on dx on dt. So it's going to be negative 2t all on 3t squared minus 1. And yeah, that's it. Okay. When they ask you, for example, find at points x equals to 2, y equals to 7, what you do is you solve for these equations. So for example, t cubed minus t equals to 2, 4 minus t squared equals to 7. You solve for t, and then sub in t into here, and that's going to be your gradient in terms of a number. All right, but I'm not going to do it because it's a very, very simple simultaneous equation. All right, related rates examples. So this is related rates, which is, I guess, where rates of change are related to each other. For these types of questions, the best way to approach it is to, how do I put it? You would write down everything you know, everything you know, everything that's given, and then what you want, write down what you want, apply chain rule, perhaps apply implicit differentiation, parametric differentiation, blah, 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 and then you'll get what you want. So in this case, The area A of a circle is increasing at a constant rate of 1.5 centimeters squared per second. What is the area of a circle? We write it down. Pi r squared equals to A. Increasing at a constant rate of 1.5. So what you have to do when you're looking at this is you have to look at the terms here. Centimeters squared per second. Centimeters squared is area. Per second is like time, right? So it's going to be dA on dt. And dA on dt, because this is area and that's time, equals to 1.5. And then find the rate at which the radius r of the circle is increasing when the area of the circle is at blah, blah, blah. So we basically say pi r squared equals to 2, because the area of the circle is 2 centimeters. And we're looking for the rate at which the radius is increasing. So that's going to be dr on dt. All right. And dr on dt, what is this? We don't know. So what we have to do is use the chain rule. That's going to be dr. Okay, so using the chain rule, we have to do things that, we have to create things that we already know. And we already know this. So that's preferably what we want to start off with, dA on dt, okay? And then dA on dt, we want to cancel out the dA because it's not in the original equation. So we're going to cancel out the dA by putting it dA here, and then this is going to be dr. So now you'll notice that we can cross out the dAs and it's going to be dr on dt again. All right. So now sub in everything you know, 1.5 times dr on dA. What is dr on dA? Over here, we can work out what dA on dr is by differentiating. So it's going to be, what is that? That's 2 pi r, like so. And then we just reciprocate it. It's going to be 1 on 2 pi r, like so. So this is going to go and it's going to be 1 on 2 pi r, blah, 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 blah. And then what you're going to do is we're going to go here. We're going to solve for, oh my God. Oh, sorry. We're going to go here and we're going to solve for r. So r is going to equal to 2 on pi square root. And we're going to sub it into here. So, okay, this looks pretty convoluted, but it's 1.5 on 2 pi times square root 2 on pi, like so. And then if you put that into your calculator, I think I actually did this already. The answer is going to be equal to 0.299. All right, so that's going to be your final answer, and that's how you find this. Okay. Obviously, there's definitely harder questions. This is just a simple example in terms of for time's sake, I guess. All right, integration. So this is a big topic. You guys hopefully are good with integration because you have to use it in differential equations, and there's going to be questions just on integration as well. So hopefully you guys are at least already familiar with this. And integration is the reverse of differentiation. When you differentiate the integral of fx, you will get fx. Basically it's saying if you differentiate the integral, you get the derivative, which makes sense. Oh, no, you just get the function itself. So the terminology now is fx, differentiate, you get f dash x, integrate, you get capital Fx. All right, that's the terminology we want to use. And when you differentiate capital Fx, it's going to go back to normal Fx. All right. So here's some applications. The definite integral of something is the area under a curve between its bounds. So for example, AB is Fx dx. This is just the integral. If this is Fx, all you're doing is you're finding from A to B, you're finding the total area underneath here. And if the curve goes under, like this, it's actually going to be negative. This is going to be a negative number, right? Negative number if it's underneath the curve. And another thing to note is, I'm not sure if they'll go too deep into this, but if you're finding a curve which dips underneath like this, and you're trying to find the area of the total area, you actually have to split your integral into here and here, and then here and here, because they'll actually cancel out if they dip under, because this is going to be positive, this is going to be negative. So you have to find this one, then find this one, flip the sign on this one, and then add them together. All right, anyways, integration. So here's some formulae. I'm not going to go over it. I really hope you guys already know this. All you do is just, do this stuff. These are the ones that was in the lecture slides, but I know that in the formula sheet they give in your past papers, there's like a lot of them, right? So definitely remember these off by heart. Don't try to don't look at the 50 formula and try to match it up. Be like, oh, this integral goes, don't have the integral here and then try to match it up with one of these, because there's a lot of them and you're going to miss some most definitely. So yeah, have these memorized. Yeah, that's pretty much it. Don't forget to add plus c to the end of every indefinite integral. Indefinite integral means there is no bound, so no a, b. It's just like this. And you have to add a plus c at the end of it. Okay, so for example, x squared dx is equal to 1 on 3 x cubed plus c. You don't include it, you lose a mark. But I'm sure you guys know that already. All right, integration. In general, you can factorize constants outside the integral. So, 3x dx is the same as 3, and then integrate x dx. You have terms added together, you can integrate them separately. So for example, x squared plus 2x dx is the same as x squared dx plus 2x dx, like so. Evaluating definite integrals, what we want to do is we want to find the integral, right? So this is the capital F is the integral. You sub in b, and you subtract it to the same integral subbed in a, and that's pretty much how you do it. The terminology is BAFX. Sorry, not terminology. The way you write it out is equals to fx, so the integral, and then BA. And then you sub in B, sub in A, like that, and subtract them. And you can split them up. Oh my god, what just happened? Let me quickly just get rid of that. Alright. Never mind, it is still blue. Oh well. Sorry, my preview is bugged out for some reason and it stays blue. But what this is saying is, if you have an integral from A to B, like this, you can actually find an intermediate point called C, and you can find the integral from A to C, add it to the integral from C to B. And that's why you can see the bounds from A to C and C to B like so. Okay? They're the same because all you're doing is adding two areas together. Alrighty. Accumulation of a quantity. If you have a quantity QT that varies at a rate of RT equals to dQ on dt, the amount accumulated / growth is calculated by RT dt equals to QB minus QA. Note that this is a rate of growth. It's not saying you're not integrating the quantity. You're integrating the rate the quantity grows. All right, and yeah, it's just an integral. That's pretty much it. Not a lot to say. When you see words like accumulation, growth, you want to use this formula. Average of a function is just given by this formula. Basically, it's just like if we look at a formula, right? What's happening is we're taking the area, but it's not really taking the area. It's taking the height of each thing, and it's dividing it by the total a minus b, b minus a, to find the length. Basically, it finds the average. If you see average, just use this formula, all right? I'm not going to go too in depth because we don't really have time for it. All right. Into density, yeah. If they give you a density, just integrate it, and it gives you the mass. All right. Not too difficult. All right. So here's a question: the temperature of a soup is increasing at a rate of RT equals to 30 e to the power of negative 0.3 degrees Celsius per minute. At time t, the temperature of the soup is 23 degrees Celsius. Find the amount at which the temperature increases between t equals to 1 and t equals to 5 minutes. Okay, so basically the temperature of a soup, right? So it's saying find the amount at which the temperature increases. So we just want the increase. We don't want the actual temperature of the soup. We just want the increase. So what you do is just do an integral. So it's the integrate 30 e to the power of negative 0.32 dt from time t1 to time t5. So we're going to do this. And the integral of this is 30 on negative 0.3t. Just refer to the sheet if you don't know how to do it. E to the power of negative 0.3t. This is your integral. This is your capital Fx. We're going to write 5, 1 here. And we're going to sub it in. So the answer is going to be, let's see. It's going to be, okay, what's 30 divided by 0.3? It's like 100, right? Yeah, it is 100. So negative 100 e to the power of negative 1.5 minus e to the power of negative 0.3. And that's going to be the answer to this question. All right. Obviously, we're going to plug this into our calculator and see what we get. And the answer should be 51.77. Okay. Very cool. Moving on. Integration by substitution. So substitution is used to integrate functions which are not considered standard. This is a very important and very powerful technique, and if you guys haven't practiced it already, make sure you practice it like 1 billion times because it's very important. Basically what this does is it solves, like, integrals aren't going to be hand-fed to you. They're not going to tell you to integrate like x squared dx in the exam, okay? Because that's just a copy the formula sheet type question. They're going to create one where it's a little bit more obscure, like x cosine. Okay, that's not a good example, but it's going to be multiple things combined. And that's when you want to use integration by substitution. So the first step is to choose a function to be u. Differentiate u and substitute everything in and solve the integral. And you know you've done a correct substitution when the result is something simpler. Look, I'm not going to write out all the steps because it sort of differs, but I'll give an example and I'll show you guys what you're meant to do. All right. So sine x sec cubed x dx. How do we solve this? So basically, first things first, when you see sec, convert it to a cosine. Not in all cases, but in this case, yes. And then what you need to do is choose a function to be your u. In this case, it actually doesn't matter what you choose to be u, because usually you choose the u to be the one which, it actually really depends on the example, but you want to choose the one where when you differentiate it, it equals to something else. So if you differentiate cosine, it's going to be equal to sine. And that's when you want to use, like, set that as u. In this case, right, I'm saying it doesn't matter because when you differentiate sine, you also get cosine. But in other examples, you're going to have to choose more carefully. So this one, let u equals to cosine x. First, differentiate this, okay? Like, differentiate straight up this equation. So du equals to cosine, actually this is going to be sine. So negative sine x dx. All right, that's your first step. And then your second step is to substitute this in. All right, substitute this into here. So what you'll notice is we already have sine x dx, but there's no negative here. So what you want to do is you want to put a negative outside and inside so that they cancel out. Sine x dx all over cosine cubed x. And now substitute everything in. So in this case, we have negative, this becomes du, so it becomes du on, and what is cosine x? Cosine x is u, so it's going to be u cubed. And that's going to be our final integral, all right? We should already know how to integrate this because this is just negative integral u to the power of negative 3 du. And this is going to be it's going to be half u squared and then plus c. All right, because it's just, This is a negative 2 here. I'm pretty sure. And then, yeah, and then what you want to do is substitute everything back in. So since we already know u was cosine x, this is going to be a half times 1 on cosine squared x plus c. And that's going to be your final answer, right? That's pretty much it for this. And yes, never forget to substitute everything back in once you're done. Integration by parts. So integration by parts is essentially a way of reversing your integration by, reversing a product rule differentiation. So basically, you know how like it's like a reverse differentiation? All these cases before don't really cover the case where you differentiate by product rule, but now integration by parts does. Also extremely important, obviously, but I'm not sure how hard you're going to get tested in the exam. It's important, but yeah, you might get a very simple integration by parts because the hard questions are pretty hard. In this case, we have to choose one function to be u and one function to be dv. So as you can see in the formula, u and dv, uv, blah, blah, blah. I'll show you guys, like you apply the formula, but I'll show you guys like a better way to interpret this, all right? Integration, you may have to apply integration by parts multiple times. Just make sure each iteration of by parts is getting you somewhere and it doesn't loop back to the same equation. So a lot of cases, right, choosing your u's and choosing your dv's, very important, because if you choose it wrong, you loop back. What I like to think about by parts is when you get two equations like this, as you can see, these are very loopy equations because when you differentiate e to the power of x, you get e to the power of x. When you differentiate cosine, it becomes cosine and then sine. So you have to make sure you choose the correct one to differentiate. Otherwise, you're going to loop back on yourself and you're going to get the same thing. All right. If you guys don't really understand what that means, try choosing the wrong thing to integrate and you'll see what I mean. All right. So here it is. Okay. So the way to choose what's u and what's v, you follow the Lie8 rule, which means log, inverse trig, algebra, trig, and exponential. And this means choose for u. So this is what you choose to be u, and then choose the other function to be dv. So in this case we have x sec squared 2x dx. Following the Lie8 rule, we have trig here and algebra here. So algebra is going to be our u. So let u equals to x. dv is going to be equal to sec squared 2x. All right. And now what you want to do is you want to differentiate u to get du, which is 1 by the way, and integrate dv to get v. So it's going to be, this is yours on your formula sheet, but it's going to be a half tan x, tan 2x, like so. And what you need to do is now go to the formula, oops, it's up here actually, and sub everything in. So u dv equals to uv, so it's going to be uv, actually I'll use a different color, uv, and minus v du. So this is how I like to think about it, all right? These two, this one gets completely ignored. You never actually use that in your by parts. But this goes to that, that goes to that. All right, it's like a triangle, and u is the important one. So what's going to happen is the equation is going to be x on 2 tan 2x minus the integral of these two, the bottom two multiplied together. So it's just a half tan 2x dx. And then this is going to be your final integration by parts. Like you still have to solve this integral, which I guess we'll do. Minus a half, this is going to be sine 2x on cosine 2x. look, I'm not gonna really go through the steps for it, but this is what we call reverse chain rule, right? But you can use a substitution as well. Do it in your own time, but the integral is going to end up being ln 1 on 4 actually, ln cosine 2x, right? So yeah, definitely give this a try. All right, differential equations finally, and we've got 20 minutes to go through like everything else. Yikes. We might go a little over time, but it's fine. So what a differential equation does is it relates a function y equals to fx to its derivatives. For example, this. The solutions to these equations are functions. You sub these functions into equations and it should all hold. Obviously, because dy and dx is, you want to sub in a function, differentiate it, and all these functions like multiplied out should give you 0. Similar to difference equations, but instead of expressing everything in terms of previous terms, you express it in terms of derivatives. So the order of a differential equation is the order of the highest derivative that appears. So e.g., if the order is 2, we have a second derivative as its highest. So for example, in this one, there's only one first derivative, the order is 1. It is linear if the y's are all linear. So this is a second order linear differential equation because the highest derivative is 2, and this is not like y squared. This is just y, not y squared, not y double dash squared. That's why it's linear. All right. How to solve a first order separable DE. So there are many types of differential equations. Wait, okay. There are many types of differential equations, and the way to solve different differential equations depend on its type. First, we focus on first order separable DEs, and these are DEs. Oops. Oh no, not again. These are differential equations where you can separate the x's and the y's by moving them to each side of the equation, then integrate it. All right, so that's why it's called separable, because you can separate the x's and the y's. For example, all right, dy on dx equals to x e to the power y, dy on dx, x e to the power y. What we're going to do is we're going to move the y's onto the y side. So this is going to be e to the power negative y, dy, and we're going to move the x's onto the x side. And what you can actually do is you can actually integrate both sides, like so. Apply the integration sign. This is going to be negative e to the power negative y, and this is going to be half x squared plus c. All right, and then what you want to do is express everything in terms of y. So in this case, we're going to actually apply like a log law. So it's going to be ln. We're going to say that negative y equals to ln negative a half x squared plus c, or minus c actually. And then y equals to negative ln negative a half x squared minus c, like so. That's going to be a final answer. And if you sub this into this equation, and if you differentiate this in terms of x, you are going to get x e to the power of y. All right? Oh, yeah. All right. How to solve a linear first order differential equation. What if we can't separate it? So this is when the first order DE comes in. This is when y and y dash are linear, but coefficients are in terms of x. Okay, so basically we have coefficients of x here. Is there an example? Nope. This example is very convoluted actually. These are in the form, yeah. So basically what happens is, you want to get it to this form. Oops. Plus pxy equals to qx. Now, the questions aren't going to give it to you in this form straight up. You have to be very careful. Perhaps you have to divide the entire thing by something. For example, if there's a coefficient, like for example, x dy and dx plus, x squared y equals to 2x. What you have to do is divide everything by x, like that. And then it'll be in this form. And then you can use this method, right? So once you get it in this form, all you need to do is first find r. Oh, what the heck? Okay, I need to get rid of this. Hold up. No. Click somewhere else. Come back. Yeah, I think here it is. Yes, we are back. So what you have to do is find Rx, which is e to the power of the integral of px dx. Literally look and find px, right? Sub it into this integral and then sub it into this equation. So it's there's a lot of Trek algebra, but you just got to do it. And yeah, it's just integration, sub everything into the formula. Make sure you, well, I don't know if it's open book or not, but just, have this open by your side or something. And it should be, I don't even know if you guys give it in a reference sheet. All right, let's solve this. So this one actually is not in terms of x and y, it's in terms of big T and small t. The idea is you have to identify which one's the x and which one's the y, because not everything is going to be given to you in this form. So dy on dx, dt on dt. So clearly y is going to be the capital T and small t is going to be the x. So we're going to get everything in the correct form. dt on dt equals to kt minus tm. And by the way, tm and k are constants, and we also have an initial condition here. So what you're going to do is we're going to move everything to one side like that, minus kt equals to negative tm, I believe, because this t is going to be representative of the y, so it's going to be y here, blah, blah, blah. And then what we're going to do is we're going to take a look at the px. So the px, this case, is the term in front of the y. In this case, the y is the t, so this is going to be our px. So integrate it. It should be negative k actually, like so. Oops, k dt. And then since k is a constant, the integral is just negative kt. All right. That should be pretty okay because it's just one term. And then what you want to do is sub it into this formula. So y, which is t, equals to 1 on e to the power of negative kt times the integral of e to the power of negative kt times qx. Qx is just the right hand side, so this is the right hand side, tm. And it's actually negative, so there's going to be a negative here as well. All right. Is that it? No, it isn't. We will now have to integrate. So negative 1 on e to the power of negative kt. Integrate this thing here. Oh my goodness. So there's actually going to be 1 on k, negative 1 on k. And then you take the tm out. And then it's going to be e to the power of negative kt plus c. Okay. Sure, I guess. And this is actually going to be a bracket, by the way. And then what's going to happen is everything's going to multiply in. So you're going to have like this cancelling out with that. So you're going to have tm on k, plus, minus, e to the power of kt, like so. And there's going to be a c here. Look, basically all we're doing is we're just, multiplying everything in. This example is a little messed up, as in there's no actual numbers in there. But yeah, that's pretty much it for this question. That's going to be answer, by the way. That's going to equal to t. And obviously, in order to find what c is, you're going to have to sub in your initial conditions and solve, like, I guess, is there a simultaneous? No, you just sub in your initial conditions and you'll find what c is. All right? Okay, let's move on. Homogeneous differential equations. All right, so this is your homogeneous second order differential equations. So now we're moving on to second order differential equations, where the right hand side is equal to 0. And these require two initial conditions or they'll be constants. So for example, a and b. All right, so let's see what's going on here. All right, so what you want to do is, like a difference equation, you want to convert the y double dashes to lambda squareds, the y dashes to lambda, and the last y as just nothing. And then you solve the quadratic. And then what you do is you literally go here and then you check if your solutions fit it. So if lambda 1, lambda 2 is a real number, lambda 1 does not equal lambda 2, then this is going to be your solution. Sub everything in. If lambda 1, lambda 2 is a real number, but they're equal, this is going to be your solution. If they're complex, then this is going to be your equation. Oh, yikes, it turned blue again. Sorry for that. I don't think you guys can see it very well, but it's just important to, I don't know if you guys actually get given the complex solution, a complex example, but make sure you keep it in the back of your head, because if the complex case appears and you don't know how to deal with it, you will lose marks. So just keep it in the back of your head. All right. In fact, I don't think you guys even do complex numbers. So maybe not. Maybe just remember the first two. All right. Solve the differential equation. So this is clearly a second order homogeneous linear differential equation. So first convert it to lambda squared plus lambda minus 6. Use maths. Solve this quadratic. What is it? It's -3. No, it's +3. Lambda minus 2. And then your solution is going to be 2, -3. All right, this just turned into a black screen. All right, I'm going to quickly fix this up. Okay, we are back. So we're going to look at it. These are obviously real numbers and they're not equal. So therefore our solutions are going to be y equals to a e to the power of 2x plus b e to the power of -3x. And that's it. All right. This is literally it. Not too difficult. Okay. Moving on. The hardest part is solving the quadratic. All right. Now we have to solve the case where the right-hand side is non-homogeneous. So the solution, oh yeah, by the way, if you have initial conditions, right, 2 initial conditions, you'll be able to find out what a and b are. In this case, we don't, but they will give you it sometimes. All right. So now we learn how to solve cases where there is a fx on the right-hand side, and the solution is different depending on values of fx. First, you must find the homogeneous solution, and then you find the particular solution by guessing solutions, and then you add them together, and that's your final solution. So it's going to be a homogeneous solution plus your particular solution. And by the way, when we say guessing, we mean like extremely educated guesses. So we're not literally going like, oh, you know, it could be 3x. We obviously make an educated guess. All right. So here it is. For example, if on the right-hand side we have -6x plus 23, it is clear that yp could be a degree 1 polynomial, because on the right-hand side over here, the left-hand side has to equal a degree 1 polynomial if the right-hand side is a degree 1 polynomial. So clearly this can't be a degree 2 polynomial. This can't be a quadratic, because a quadratic and a degree 1 polynomial will never be equal. All right. So blah, blah, blah. I'm not really going to talk about your guesses too much. I would like to, but we don't really have time. So I will give you, I think I have a list of guesses. Yes, there is a list of guesses here, so it doesn't really matter. But yeah. Oh wow, this slide is repeated twice. I never even knew that happened. Okay. So if right-hand side is a polynomial, your guess will be a polynomial of the same degree. ax cubed plus bx blah, 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 blah. If the right-hand side is an exponential, then your guess will be a similar exponential, but with a constant in the front. If it's a sine or cosine function, your guess will be a alpha or a sine 4x plus b cosine 4x if it is sine 4x. If it's just sine x, then these are going to be sine x's and cosine x's as well. Be very, very careful to remember this one, because this is one people forget a lot. When the thing is sine, it's not just sine. It's also sine plus cosine. All right? So definitely remember that. And there are some which you cannot guess. All right? And then once you have your guess, sub it into the differential equation, and that's going to be your answer. So let's quickly do this example, extremely quickly do this example. Let's see. So this, you'll notice, this is actually the same as the equation we solved up here. So, see. except the right hand side is 36. So what's good is we already have our homogeneous solution. So now what we want to do is find the particular solution and add it to this one. All right, let's see. Question, what if the right hand side equals to sine 3x plus cosine 3x? I came across a question like that and I don't know what to guess. Okay, so I'm pretty sure if the right hand side is that, then you guess the same thing. Just guess this. All right, because this thing here takes into account sine, cosine, and sine plus cosine. That's what it wants to cover. This covers all three. In this case, for example, if it's only cosine, right? If the answer happens to have only cosine, the beta will become, like alpha will become 0 and you'll only get cosine. This is like really flexible. So it should cover everything. If I'm wrong, let me know, but I'm pretty sure. I'm pretty sure that should be your guess. Anyways, let me think about it real quick. Yeah. Oh yeah, it should work, it should work. All right, so, alrighty, let's see how we do this. So what we need to do is just make a guess. This is going to be alpha x plus beta x. Sorry, just plus beta, because it's 36s x on the right hand side. So we're going to guess a first degree polynomial. And then we're going to sub it into alpha x plus beta. So we're going to sub this into our differential equation. So this differentiated twice is 0. And then this differentiated once is going to be alpha. And then minus 6 times alpha x plus beta equals to 36x. What we're going to do is now we're going to have alpha minus 6 alpha x minus 6 beta equals to 36x. And then what happens is you want to equate the coefficients. So this is degree 1, this is x. Equate them. Negative 6 alpha equals to 36. And then this is actually a plus 0. So what you want to do is alpha minus 6 beta equals to 0. And now we have a simultaneous equation. Obviously alpha is going to be negative 6 and beta is going to be 1, I believe. Yeah, beta is going to be 1. Oh, what the heck is going on? No, it should be negative 1, shouldn't it? Yeah, it's negative 1. Beta is going to be negative 1. Alpha is going to be negative 6, just from solving this. And then, therefore, your particular solution, so yp, is going to be equal to, what's going to be equal to? It's going to be equal to, oh yes, this. So negative 6x minus 1. Therefore, what you would do is you write the final solution as a e to the power of 2x plus b e to the power of negative 3x and then minus 6x minus 1. And that's going to be your final solution. If you have initial conditions, this is the time to sub them in. All right? And yeah, that's pretty much it for this question. All right? All right. Now, systems of first order linear, blah, blah, blah. Okay, so now we can have systems where it satisfies multiple equations and have to find a solution that satisfies all. The method, similar to solving a normal simultaneous equation, we rearrange, differentiate, substitute to obtain one equation, hopefully a differential equation we can solve, and then solve for one variable. And then once you find y, substitute this back into our original system of equations to obtain the solution for x. So here is an example, all right? Given that x blah, blah, blah. Look, I would love to go over this, but this is actually a pretty long system of equations. I'll solve a little bit of it, but I'm not going to go through all of it because this one actually takes a while. So what happens is first, we're going to let dx on dt be x dash, right? And similarly, y dash for the other one. So x dash equals to x plus 9y. Y dash equals to negative x minus 5y. What you need to do is now try to combine these two. So in this case, I'm going to try and combine. I'm going to try and substitute y dash into this one here. So we're going to differentiate the very first column. So x double dash equals to x dash plus 9 y dash. And then we can now sub in y dash because we already know what y dash is. So we have x dash plus 9 negative x minus 5y, like so. And yeah, and then we're going to just bring this out. So x dash minus 9x minus 45y. And then now we're almost good. We want to express everything in terms of x, right? Because what we're doing is we want to get a differential equation. So what is y? We're going to go here. We're going to look at our equations. Y, okay, so y is actually going to be equal to x dash from the first equation here, 1, x dash minus x all on 9, like so. So then you're going to have your final equation, x dash minus 9x minus 5x dash plus 5x. And then combine everything, and you're going to have a second order linear differential equation, which you can solve using the methods we learned before. All right? Convert it to a quadratic, blah, 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 blah. And what you're going to get after you solve it is the solution is going to look like, let me see. I think I did this already. Did I? Oh no. Don't tell me I didn't. Here it is. You're going to get x equals to a e to the power of negative 2t plus b e to the power of negative 2t. Because solving this quadratic gives you a solution of x equals to negative 2. And then if you follow it, since the two solutions are the same, you have to multiply a t to it. Don't really worry about this. I don't think you guys cover when everything's the same, but basically when you solve for lambda 1, lambda 2, both equal to 2. So when you're doing this form, you have to multiply an extra t to it to make them different. Because if it was just a e to the power of negative 2t plus b equal to negative 2t, they just combine, right? They just combine. It's just a plus b. So you have to multiply t to it. All right, anyways, enough with that. And then what you need to do is substitute into this equation here, right? Or actually any equation, just substitute x, differentiate it, blah, 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 find y, and that's going to be your final solution. And if you want, if you're feeling brave, you can also substitute in these initial conditions. But we have to move on because we have more things to cover. All right, methods of approximation. Newton's method and bisection of the interval. Try to stick to exact values. That is what we usually try to do. However, there are a lot of situations where we cannot find exact solutions. So Newton's method and the bisection of the interval method is used to find approximated solutions to an equation. This is the intermediate value theorem. If f is a continuous function on an interval ab, with fa and fb differing in sign, there is at least one solution. What it's saying is, if we have a function like this, yeah, this is going to be negative. If this is negative and this is positive, if they switch signs, there will be a root, okay? And I mean, like that's a pretty obvious thing. Like that's pretty obvious. If they switch sides, then it crosses the axis and there's a root. Wow, how amazing. But the thing is, when you're doing intermediate value theorem, state that f is continuous, or you might lose a mark, because if f isn't continuous, the function might do this, right? It might just jump and it might not have a root. So state that f is continuous when using the intermediate value theorem. Number 2, bisection of the interval. Basically, what it's saying is we can just approximate a solution by repeatedly halving the interval where a sign change occurs. So what we do is, right? What we do is, if I get an example of a function here, right? It's going to look like this. We're going to have this. We're going to have this. We're going to evaluate this function at fa. This is going to be fb. This is going to be negative. This is going to be positive. So what you want to do is, you want to half the interval. So bam, we slid it in half. and then we compare the point here, and now we see, compare where the sign changes are, right? And for example, this is going to be positive, this is going to be negative. So we have to compare these two again. Pretty much get rid of this and then do the same thing we did on this, right? And we're going to do it again. We're going to half the interval. Let's half the interval like this. And we're going to take this point here. This point here is going to be negative. This one's going to be positive. So we get rid of this and we zoom in on these. And we're going to keep halving until we get to the root. And the root of all things is going to be this point here. Sorry if I'm using a lot of random colors and it's messy, but hopefully you sort of understand the logic behind this question. So, okay. Alrighty, so, wait, is it time? Oh, it is time. But we have more to go, so hopefully I can go over time. Alright, let's see. Newton's method. Okay, so, oh yeah, this combines them both. So, basically, Newton's method, let fx be a differentiable function. If you know a value, x0 is close to a root, we can repeatedly apply this formula here to obtain a solution that is closer and closer to the true value of fx equals to 0. All right, and I really want to go over the theory behind this, but basically, be very careful. If the point you choose is too far away, you might end up getting a wrong approximation. So make sure it's close to the place. So basically, how Newton's method works, right? If you have a function here, well, actually, we'll make it a simpler function, like that. Well, actually like it like this. All right. So what it's doing is it's saying you start at a point x0, right? And what we're saying is this has to be close to the root. Close. And this is the root. This is close enough. So what it's doing is it's drawing a tangent and it's hitting the axis like this. And then what it's doing is it's going to, and then this is your one application. So what it's going to return is xn plus 1 is going to be here. It's going to be x1. And then what it's going to do, you're going to do the same thing again. You're going to go up to the function. You're going to draw a tangent. It's going to hit here. This is going to be your x2. And then basically what it's doing, it's going to the tangent and it's going closer and closer to the actual root here. That's basically what Newton's method is doing, all right? But the problem is, if you have a function like this, I want to approximate this root. If you choose this point here as x0, you're going to end up approximating this root over here. You're not going to approximate this. So what you have to do is make sure it is close, all right? Make sure you choose Newton's method close. And usually they'll provide a Newton's method that's close. Or they might ask you, oh, why is this approximation wrong? And you can let them know. All right. So we're going to approximate a solution for fx equals to x cosine x minus x squared using bisection of the interval method. So approximate a solution. Okay, that's fine. Bisection of the interval method. Let me just, Abdullah, we don't have any like other lectures today, right? So it's fine to go overtime. But anyways, that was a question, by the way, guys. Approximate a solution using bisection of the interval method. So what's going to happen is, first, we're going to draw up a table. So honestly, you can draw up this table any way you want. I have like this really rigid way I like to draw it up. It's just this. We have one at 3 p.m. Okay, I'll wrap it up soon. Okay, so it's going to look like this. Yeah, that's fine. Okay, I'll wrap this one up soon. So what you're going to do is you're going to put 0.5 here. You're going to put 2 here. I like to draw a dot every time this is not values. So basically 0.52, I'm going to plug this into my calculator, blah, blah, blah. For example, 0.5 times, 0.5 times cosine 0.5 minus 0.5 squared. All right, I'm going to get a calculator, blah, 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 plug it in. And that's going to give me 0.188. And this is, okay, and I've already calculated these values, so this is going to be 0.48, negative 4.8. And then what we're going to do is, we're going to find the interval that's the average of these two, right? Because these switch in signs, which means there's a root in between them. And since there's a root in between them, it's going to be 1.25 here. All right, we're going to halve the interval, and we're going to evaluate at 1.25. So evaluating at 1.25, we get negative 1.16. And now you can see this is negative. Since this is negative, that means there's a root in between the negative and the positive, which means we want to take these two. So we're going to go back here, 0.5, 1.25. And we do the exact same thing. 0.5, we already know what it is. We already know what 1.25 is. And then we're going to halve this interval. And the half of this interval is 0.875. And that's going to evaluate to negative 0.204. And as you can see, these are both negative again, right? So we're going to take these two. So blah, blah, we're going to do it again. Blah, blah, 0.875. And then we're going to do it again and again and again. All right. And obviously, if this here was positive, we would take the other two. We would take these two instead. And we're going to take this and that. But basically what happens is these values here, 0.875, will get closer and closer to the true root of the answer. All right. That's pretty much it. And Newton's method, what you do is you go to your calculator and you just type in this formula. So what I do is you go here, we go answer. I'm going to write out what you type in the calculator. Minus, and then this, so it's going to be answer times cosine of answer minus answer squared. And then you're going to differentiate this and put it on the denominator, which is going to be cosine answer. Well, what is the differentiator? Cosine answer minus, oh my god, sine answer times answer minus 2 times answer, right? And then what we're going to do is we're going to go in the calculator, plug everything in. So I'm going to quickly plug everything in. So answer minus answer times cosine of answer times answer squared. Hopefully my integration was right. Sorry, differentiation. Cosine times answer minus sine answer times answer minus 2 times answer. And then what you want to do is you want to plug your answer as 1. And then you basically press equals like 100 times. And once you press equals 100 times, that's going to do like 50 iterations of this Newton's method. And it's going to give you a really accurate result. So the actual root is 0.79 blah, 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 right? And yeah, that's what my calculator gives. It should be pretty accurate, like to 10 decimal places. As for our bisection of the interval, we got sort of close. We got given an interval of 0.5 to 2 and 0.75 was what we ended up with. So, that's close enough. Okay, so now we can move on. That's basically it. So now we have Maclaurin series. Maclaurin series is just, sometimes there are functions which are very hard to deal with. On the other hand, polynomials have been very easy to deal with. The idea of the Maclaurin/Taylor series is to approximate functions with polynomials. So basically we're saying complex functions can be represented as polynomials, which is true. Like if a function looks like this, we can actually create a polynomial that also looks like this. And that's what they want us to do. Like it's not going to be exact, but you can. And yeah, Maclaurin series of a function fx is given by this, where fn is the nth derivative of fx. So basically, if I want to find the nth term, I'm going to have to derive it n times, which is kind of a trick, but I mean, you got to do what you got to do. So it makes things a lot easier. So yeah, f0 and then sub in 0. And then, as you know, the x's go up. For example, x squared divided by 2 factorial, blah, blah, blah. And that's pretty much it. All right. Not too difficult, because it's just subbing into a formula. So some common examples of Maclaurin series include this 1 on 1 minus x, which is just 1 plus x squared, blah, blah, blah. E to the power of x, which is this, except the constant in front is always 1, which makes sense, by the way, because when you derive e to the power of x, it just becomes e to the power of x, like so, right? And then when you sub in 0, it's just going to be 1, 1, 1, 1. So it's just going to be 1 times x1, 1 times x squared, 1 times x cubed, blah, 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 blah. And then, yeah, sine and cosine. All right. Find the Maclaurin series for y equals the tan inverse x up to the term for x cubed. Okay, so we have tan x, tan inverse x. That's your first derivative. Oops, that's your f. First derivative is 1 on 1 plus x squared. Second derivative, and then we need to find the second derivative and the third derivative. All right, look, this one's just going to be negative 2x on 1 plus x squared. That. And this is going to be some really convoluted thing. It's going to be some long thing. Actually, wait, it's going to be the quotient rule. So yeah, so that's going to be your derivatives. And then what you need to do is you need to sub in 0 into all of them. So, and then find what they are. 0 into tan x is 0. F dash 0 into this one is going to be 1. So it's just going to be 1 times x. So it's just going to be x. You're going to get f double dash times x squared. So 0 is going to be 0 plus 0. And then over here, we're going to sub in 0 as well for our x cubed on 3. So 0, 0, 0. It's just going to be negative 2. Okay? So it's going to be negative 2 times x cubed on 3 factorial. So what you're going to actually get is the final thing is going to be x minus x cubed. Oh my goodness. X cubed on 3. Because 3 factorial, the 2 cancels out. And that's going to be a Maclaurin series for tan inverse x. All right, very cool. And now we are finally moving on to partial differentiation, which is almost to the end. This is our second last topic. Basically what's happening is we have a 3D function if z equals to fxy. So if I draw a plane like so, right, the 3D function is saying at every single point xy, we associate it with a height, right? Sometimes it'll be higher, sometimes it might be lower, like that, right? And then what's going to happen is we're going to have a plane that comes down like that. And then at every single point here, everything's going to have a height, basically. And it's going to create a 3D shape. And what partial derivatives means is when you do dz on dy, okay, this is actually del, but I'm going to pronounce it as d anyways. Dz on dy, it's finding this rate of change in the y direction. Okay, so for example, if I move a little bit, like how much does it change in y? Blah, blah, blah. Okay, rate of change. That's what differentiation is. So basically, partial differentiation is very easy if you're good at normal differentiation. All you need to do is differentiate it with respect to y, treating everything else as a constant. So this example is a little, I wonder if there's an easier example. Okay, I'm going to do this, and I'm going to differentiate in terms of y, right? So dz on dy. So what we're going to do is, this is in terms of x, we treat it as a constant, so it goes to 0. This is the same as a number, like 8, right? If we differentiate 8, it goes to 0. Differentiate 2x squared, it goes to 0. Now this, we differentiate in terms of y. So it's going to be 2x. The y just disappears. Then plus 4y minus 6, which is, this is just a constant. There's no y, it goes to 0. All right? And in this, and as for x, dz on dx, we also do the exact same thing, except treat all the y's as zeros. So, for example, let's see, 2x becomes 4x plus 2y minus 6, like so. All right? And that's pretty much it for partial differentiation. You can also do it again and again. Like you can do, if I go, for example, if I want dz on dy dx, what it's saying is differentiate in terms of y, and then differentiate in terms of x, like do it over it, right? So in this case, we're going to differentiate this in terms of x, so it's going to be just 2, all right? Anyways, moving on. You guys should try to do this in your spare time. It's just It's just, I mean, it's not too difficult, okay? It's just like product rule. All right, so critical points. This is our very, very final slide of content. If we are given z equals to fxy, a function in two variables, how do we find where it attains a maximum and a minimum? At any point where it has both this equals to 0, like the partial derivatives equal to 0, we will consider this. So basically what it's saying is, in our graph here, all right, if we have a graph, a 3D graph, that looks like this. Okay, it's like a curve, all right? Pretend this is a 3D, like upside down bowl, all right? Basically what it's saying is that if in the y direction it's 0, in the x direction it's 0, right? In all these directions it's 0, then we're going to achieve a critical point. And what it's saying is this has to equal to 0, and this has to equal to 0, and therefore there'll be a critical point. And then what you're going to do is you're going to sub in these derivatives into the equation, d, right? Literally, like this looks pretty complicated, but it's really not. You just differentiate it, sub it into this thing, and then go to the criteria, and bam, you're gonna determine if it's a local minimum, a local maximum, or a saddle point. All right, so let's do that. All right, let's solve this. So this is a simultaneous equation. If you solve the simultaneous equation, what is it? Okay, it should be 2, 1. All right, that's going to be your critical point. And then what we have to do is we also have to differentiate 2 times in terms of f. We have to differentiate again. So we have to do, because these are second derivatives. So I'm going to quickly write them out. This is f y y. This means 2 times like the derivative of y. It's going to be 4. Fxx is going to be also 4, and as we can see from here, fxy is going to be equal to, this is fxy, all right, just shorthand, is going to be equal to 2. And then we're going to plug them in. So this one is going to be, let's see, this is xx, so it's going to be 4 times 4 minus 2 squared, and that's going to be 12. 16 minus 4, yeah, that's 12. And then now let's take a look at what sort of stationary point it is. D is greater than 0. This is D, by the way, just letting you know. D is greater than 0. The double x is greater than 0. Let's see. Yes, it is greater than 0. Therefore, there is a local minimum. Therefore, we can say local min at, where is it? 2, 1. All right. And that's pretty much it. We're saying there's a local minimum, so it looks like a bowl like this. If you draw it in 3D-ish. A saddle point literally looks like a saddle. I don't really know how to draw a saddle, but a saddle is actually a fake critical point because it's not a minimum nor a maximum. It just has like 0 for its derivatives. But yeah, that's pretty much it. This is a local minimum. And yeah, so therefore this function only has one critical point, which is a local minimum. And yeah, that's all, folks. Thanks for tuning in today, guys. We all wish you the best of luck, and I hope everyone gets the marks they deserve. Good luck in your final exams from the entire MathSoc team. And yeah, I hope to see you guys again. And I'm very sorry that this seminar was rushed, but this course is just extremely packed with content, and we can't fit it all in 3 hours. But yeah, thank you, and I hope to see you guys, well, if you guys decide to take more math courses.